Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're going to finally get into some aspects of astronomy that have been around us for a long time, and that is the nature of the spectra of stars. So the stellar spectral types and how we interpret their spectra. It's the beginning of the understanding of the nature of what stars are, and so let's talk about that right now. Well, what are stellar spectra? If you take the light from a star and you break it into a prism using a spectrograph or something, you take the light from a star, put it through some sort of slit, let the slit then go onto a prism or in a shell spectrograph or something, you'll break apart the light into a rainbow color. And every single kind of star has a unique fingerprint, not unique, but I mean unique for its type. And so different stellar spectra have different appearances. Now, it was thought for a very long time that these things were all very random, but yet patterns were discovered. And it's the discovery of those patterns that we'll be talking about today. So the types of stellar spectra we see here in this diagram show us that we have various kinds of spectral types. On the left-hand side is the spectral type running from O to M with a couple of others at the bottom, and then the catalog listing. Now, if we look at the spectra, these are photographic color prints of the spectra, and we can see that the blue side there's a blue end and a red end. And we see that for the O-type stars, they're significantly brighter in the blue than in the red. And for the M-type stars, they're significantly brighter in the red than the blue. We also see kind of a gradual progression of dark lines in the spectra, meaning absorption lines that appear inside of each of the spectra. And they change with spectral type. So let's see what all that means. All right, so first and foremost, stars actually do have color. So if you go outside into a dark night and look at stars, if you look at, say, Albireo, which is Beta Cygni, and you go and look at it through a telescope, what you'll find is that those two stars in the sky, actually it looks like one in the sky, but if you look at it through a telescope, you can resolve them into two. One of them's gold, one of them's blue, and so stars have color. They definitively have color. So stars are basically big, hot balls of gas. They're just the same thing as the sun, except really far away. And when we look at some star that's very, very, very far away, we notice that it has a certain color. Stars themselves, because they're hot and big and dense, they're huge like the sun. The sun is 1,000,000 times bigger in volume than the Earth and 100 or so Earth diameters across, so they're really big. Anything that's really hot and really dense emits a continuous spectrum. And the continuous spectrum comes from below from the photosphere, the lowest visible layers of the star. And that spectra is really close to a black body, which can be described with a single temperature. Now, if a star has a black body spectrum, then from Wien's law, which we talked about some time ago in another video, from Wien's law, we expect that hot stars appear blue and bright, and medium hot stars will appear yellowish, and cooler stars will appear red. So, we'll go back and look at Wien's law. So what the heck was Wien's law? Wien's law showed that the peak wavelength at which a black body radiates is inversely related to its temperature. So the hotter it is, the shorter the wavelength. The cooler it is, the longer the wavelength for the peak of the black body spectrum. This means that if we look at extremely cool objects in deep space, such as dark molecular clouds, they'll be peaking way out in the infrared, and their temperatures will be very cool. So they'll have long wavelength light that they'll be emitting mostly at, and their temperatures will be very low. When we go up to like solar type objects, the temperatures are relatively high, about 6,000 or so Kelvin, and the wavelengths are roughly in the range of about 5,000 angstroms. So that's invisible light. So these are shorter wavelengths than infrared. And if we go to extraordinarily hot objects, such as X-ray emitters, they can be emitting primarily out in the X-rays or in the far ultraviolet, and that would be a very short wavelength, but the temperatures are then very high. So Wien's law just simply says that the peak of the wavelength of a blackbody spectrum is inversely related to its temperature. All right, so the spectra of stars then are determined by the peak of that blackbody spectrum, or at least the fact that there is a blackbody spectrum below an atmosphere of the star. So the star isn't like a solid object and here it begins and there it ends. No, we've seen from the sun, if you look at an eclipse, that the sun has a photosphere, the sun has a chromosphere, it has a corona, it has a solar wind. All of the materials of the sun come off of the sun as a solar wind. So there is an atmosphere to the sun. So likewise, there is an atmosphere to every star. And that atmosphere is by definition cooler than the interior of the star. So it's absorbing the light and re-radiating it at other locations. Well, that produces an absorption line spectrum according to Kirchhoff's laws of spectroscopy. So we can use, or at least we think we can distinguish different kinds of stars from their spectra. So when people first invented photography, way back in the latter part of the 19th century, people were looking at the stars, taking pictures of the stars, taking spectra of the stars, because what the heck, why not take a spectrum of a star to see how bright it is at various wavelengths? And people made catalogs, huge catalogs of stars. So the spectral classification of stars happened well before photography was invented. It started in the 1860s by a Jesuit astronomer in Italy who observed with a prism just to his eye about 4,000 stars or so, and he divided them into 4 rough groupings, and he found that there was common spectral absorption features, meaning dark lines that he could see. So he was doing this all by eye with no photography, and it's very interesting that he was able to group them into various things. So that's 1860s. Between the 1880s and 1890s, the Henry Draper Memorial Survey at Harvard University, it carried out a systematic photographic study of all the stellar spectra over the entire sky. This was an enormous undertaking, effort which was led by Edward Pickering at Harvard. So this took at least a decade or plus to actually make all of these things. They used objective prism photography, and remember that photography was invented in the latter part of the 19th century, and so using prism photography, he was able to take from the telescopes both at Harvard University and down in Peru. They obtained about 250,000 spectra of 250,000 stars. And what they then did is they said, well, we're going to take all these spectra and we need to organize them. I mean, there's 250,000 for goodness sakes, and it's going to take a long time. So what they did is they hired a series of very intelligent women as computers. That was their job title, a computer. And their job was to analyze these spectra. So the women got in a room and started working on it, and Edward Pickering hired a large number of women to do this analysis. And in 1890, Pickering and Wilhelmina Fleming started their first attempt at spectral classification. First, they sorted the stars by the hydrogen absorption line strength. So they looked at how strong the hydrogen absorption line, and they said, well, the A stars have the strongest hydrogen absorption lines. And they went farther and farther down with weaker and weaker hydrogen absorption. So that was mainly their goal, was just to organize them by hydrogen absorption. The problem is that as it got weaker and weaker, there were other lines that kind of just magically appeared. And so deciding which lines to actually classify them by, because you started with A, B, C, D, E, F, and you say, well, they get weaker and weaker, but then other lines start protruding in. So therefore, they knew that they didn't have the final answer, but they didn't know what the answer really was, and their best guess was the hydrogen absorption line. So that's what they stuck with. But rearranging those spectra was a major undertaking. Approximately 11 years later, in 1901, Annie Jump Cannon noticed that the stellar temperatures were the principal distinguishing characteristic among the spectra. So what she did is she took all this arrangement, the A, B, C, D, E, all the way down, and she rearranged them instead of by hydrogen absorption line strength. She removed most of the classes as being redundant, and she reorganized them according to decreasing temperature. So she found the O stars to be the hottest temperature, then the B's, then the A's, F, G, K, and M. And these are the 7 primary stellar spectral classes that we recognize today. It was an enormous undertaking that she did, and this reorganization was enormous. Later work she added, there were other stellar classes like R, N, and S that were later added, but those have been recently discarded and no longer used. But we use different types instead today. But her organization of these things in 1901 was a major undertaking, and it actually gave us significant understanding as the nature of stars. So when she published her catalog of stars in 1901, she was then considered one of the most influential astronomers of the 20th century. And she is definitively one of the most important astronomers of the 20th century, primarily because she had access to the data and she knew what to do. And she did something that no one else had done with enormous undertaking, with enormous data sets, and discovered something truly fundamental, which was that the stellar spectral sequence is a temperature sequence. That's the trick. So you can organize them from O stars as being hot to M stars as being cool. And she used basically Wien's law to do it of black bodies. She lived between 1863 and 1941. And she eventually, over the course of her entire career, classified over 500,000 stars. So, wow, that's a lot of work. 500,000 of anything, of any activity is a very hard thing. If you suspect, just put it together, just do it in your head and think, imagine that it took 1 to 2 minutes per classification. And if it's, just say 2 minutes, just because she was faster than that, but imagine it took on average 2 minutes. So that ended up being 1,000,000 minutes of stellar classification throughout her entire career. Wow, just astonishing. There's a reason why the Annie Jump Cannon Award for the American Astronomical Society is one of the most prestigious awards that one can be bequeathed for lifetime research in astronomy. All right, so her stellar spectral sequence was incredibly important, and we cannot overstate its work. It classified them from O's, which are brightest in the blue, to M's, which are brightest in the red, comparatively. Well, what she then did further is that between about a decade later, she created subclassifications. So she further divided each stellar spectral class into subclassifications, such as with a number at the end from 0 to 9. And these things were gradations of A star. Let's say we start with an A star. And so the highest temperature A star was an A0. The lowest temperature A star was an A9. And she took another 13 or so years, applied this concept to the Harvard classification scheme to about another quarter million stars. And this was then published as the Henry Draper catalog. Henry Draper, why not Annie Jump Cannon? Well, Henry Draper was the one who was running the program at the time, so it became the Henry Draper Spectral Classification System, and this system has been adopted by pretty much every astronomer globally, worldwide, as the way to classify stars. So it is a global standard for everyone, and it allows astronomers to talk to each other about the types of stars, what they are, and how they're classified. And this is a very important undertaking, and it's recognized worldwide as being an incredibly important thing. All right, so now we look at the stellar spectral classifications individually, and we say, well, why are all the absorption features different? What's the reason for their difference? Why do they exist? Why do these stellar spectral classifications even exist? So it was first thought that the composition of the star was the thing that determined the absorption. Because that makes sense. If you put, say, sodium in a Bunsen burner and look at the gases that come off, you see emission lines of sodium. And so likewise, if you do a very, very, very hot source of light behind the sodium vapor that's coming off after it glows and is just floating upwards cool, you'll see sodium absorption in the hot light as on top of a continuous spectrum. So it's totally natural to think that the absorption lines in a star would be directly related to the composition. And that's what was thought for a very, very, very long time. So therefore, people thought that A stars were primarily composed of, say, hydrogen, and M stars were primarily composed, in their atmospheres at least, of oxide molecules of different elements, such as titanium oxide and vanadium oxide and carbon monoxide and all sorts of other things that could be, where spectra could be obtained. However, that's wrong. And that's interesting how that's wrong. And the person who discovered that that was wrong was a graduate student. She was at Harvard too. She was one of the computers, and her name was Cecilia Payne-Gaposchkin. And in 1925, her doctoral dissertation was published as a book, Stellar Atmospheres. And it was quite literally one of the most breakthrough understandings in the nature of what stellar spectra are. She used the rising concepts of quantum mechanics, which were being discussed and debated down the hall from where she was working. And she said, well, wait a second, it's not about the composition, it's about the excitation. So every atom has different excitation levels, with hydrogen needing a huge amount of energy in order to excite the electrons out of the ground state. And so if you have hydrogen excitation, you need it to be very hot, such as an A star. But if it's too hot, then they get ionized and it decreases again. But if the photon field isn't energetic enough, then you don't get any excitation at all, such as in the cool stars. And if it gets cooler still, then molecules can form and you get molecular transition lines. But that doesn't change the fundamental composition of the star itself. She discovered that stars were primarily composed of hydrogen and helium, and that was their stellar composition, but only the relative abundances of, only the temperature was what determined what the absorption features were. So if she assumed, and she assumed roughly rightly, that stars are roughly the same chemical composition with dominantly hydrogen and helium, then the stellar absorption features are due entirely to the temperature of the background photon field. And that was her breakthrough analysis using the understandings of quantum mechanics and how much it takes to excite atoms at various temperatures in gaseous states. So that was become one of the most important things, and it's still very good reading today, and it's a good way to actually understand the nature of stellar spectra is by reading her dissertation from 1925, Stellar Atmospheres. So that was the reason for it, and the composition is not important. It's not really the thing. It's only the difference in temperature that makes the important thing. As some examples, B stars are the hydrogen is almost all completely ionized, so you get very weak hydrogen lines. A stars, you get the maximum excitation temperature so that they get out of the ground state, they go to first and second and third excited state, they drop back down and they re-radiate their light in other directions. G stars, too cool, there's not enough photons, the photons are not energetic enough that exist. There's not enough energetic photons in order to excite the hydrogen out of the ground state and into excited states such that they can absorb at that frequency. So that's the reason for the hydrogen lines. And then if we go further on, we find that, well, let's jump forward a bit further in time. Right in the latter part of the 1990s and 1999, a couple of different stellar classifications were added, the L's and the T's, which are much, much, much cooler. They're cooler than the M stars. They're about under 2,500 Kelvin. And they're starting to show up radically in digital, extraordinarily sensitive, infrared, full sky surveys. They're so very, very cool that they emit mostly at infrared wavelengths, and L-type stars are between about 1300 Kelvin and about 2500 Kelvin in the light in their temperatures. They've got lots of molecular absorption, such as chromium hydride and iron hydride and lots of neutral metals, but also some strongly bound molecules such as titanium oxide and vanadium oxide. So these bands of spectra are really there. However, if you go even cooler, sub 1300 Kelvin, you get what are called the T dwarfs. And the T dwarfs are really strange. They've got methane and ammonia, and they could be considered failed stars. These are the brown dwarfs. The difference between a T dwarf and Jupiter is really fuzzy. And so that's a boundary area of current research, is trying to understand that. We don't think that most of the T dwarfs are massive enough in order to ignite hydrogen in their cores to make them actually stars. So the boundary between a T star and a red dwarf and a dwarf star, or specifically even a brown dwarf or a Jupiter, is very fuzzy, and it's an area that people are looking at entirely today. Okay, so go back in time again. So this is forward. Now we go back to like 1943. And Morgan and Keenan added a second level to the spectral classification system. And what they discovered is that not only did stellar spectra, the two stellar spectra could have exactly the same absorption features, except that one set of absorption features lines were wider than the others. So you could have different widths of lines for exactly the same temperatures. And what they discovered then that they classified them into 6 general groups. We call, which there are supergiants, giants, bright giants, giants, subgiants, and dwarfs. And so those 6 classifications that we see today are based on the widths of the lines. So not only is there a temperature profile, but there's a width profile. And this spectral classification, this subclassification, this luminosity class, has always added to a star if you can do it. So the sun is a G2-5 or G2 dwarf. Betelgeuse is an M2 supergiant, or M2-1b. Rigel, another wonderful bright star in the sky, is a B8 bright supergiant. Sirius, one of the brightest star in our night sky, is an A1 type star, and it's also a dwarf or a main sequence star. Aldebaran, which is another prominent red giant star, is a K5 type star, and it's a giant type star. So these kind of things are based on the widths of the lines, and you compare them between various types, and you can see the difference. It's prominently displayed in digital sky surveys because you can get much more greater resolution. Why is this all important? So we're just looking at stars and classifying them and putting them together. Well, stellar classification is probably the best way to get to understand the physical characteristics of stars. When you don't really know anything about anything, what you first do is you group them by their appearance, which is what was done initially back in the 1860s and 1880s and 1901s, and that was the goal. Just arrange them in some logical order. And all of a sudden, by arranging them in order, you discover, hey, wait, those arrangements of the stellar spectra are based on the physics of quantum mechanics and how atoms react with each other. So the spectrum uniquely identifies the star, because you can look at thousands of stars. And they've looked at hundreds of thousands, and hundreds of thousands have been classified. And we find that they fall into these groups. There's nothing else besides the O, B, A, F, G, K, M, L, and T's, and anything like that. They are the primary classifications. They can be put somewhere in there. There's no other real weirdos. We can call carbon stars weirdos or white dwarfs weirdos. But other than that, we really can't say that there's anything that's like, oh, that's a star, but what the heck is it doing? It's only emitting at one wavelength. That would be really weird, and it doesn't happen. So there's something fundamental that it tells us about the star. We learned that they are opaque, hot bodies with an atmosphere above them with absorption lines, and we now understand the process of that. So stellar spectral classification is the first, most basic tool, and it's incredibly important for understanding the physics of stars. So people come along for a long time and they say, well, let's find out how we can remember this, because undergraduates in astronomy have been trying to remember O, B, A, F, G, K, M for a very long time. And you can come up with all sorts of funny mnemonics, and some of them are good, some of them are bad, some are PC, some are not so appropriate today. But if we look at the old ones, say from Harvard in the 1920s when they became it, and it was, time is, oh, be a fine girl, kiss me, or oh, be a fine guy, kiss me, whatever you have. But people have come up with new ones. My favorite that I came up with is Overseas Bulletin, a flash, Godzilla kills Mothra. I like that one. That's fun. And there's all sorts of other ones. You can make up your own, lots of different things. And if you post them on the YouTube channel, that would be cute. So make up one, post it here. I'd love to see it. All right, so let's look at these stellar spectra specifically and look at specific examples of stellar spectra. So let's start with the O stars. We find that they're so very hot that they peak in the ultraviolet. And in the survey that I'm looking at, this comes from the Sloan Digital Sky Survey, and I'm looking specifically at data release 5, and I'll look at a few spectra from data release 5. So we got the O stars. They're so incredibly hot. They peak in the ultraviolet, and they peak outside the range of the spectra of the stellar of SDSS. And that means that we have very strong ionized helium lines, and the temperature is over 30,000 Kelvin. And hydrogen lines don't exist. Why? Because all the hydrogen ionized, so you can't get absorption if you ain't got an electron in the atom. So that's why you don't get hydrogen absorption in O stars. Now if we look at B stars, we start seeing hydrogen absorption features, but they're weak. And then you also have some neutral helium, because helium is strongly bound, but not as strongly bound as hydrogen. And so we get neutral helium as opposed to ionized helium, and the lines of hydrogen get stronger and stronger until we get to the A stars that are cooler now. Now we've cooled down to about 10,000 Kelvin, so we get very, very, very deep absorption features in the due specifically to hydrogen in the stellar spectra of A stars. When we get to F stars, the hydrogen absorption starts to get weaker because the temperature is cooler, so you have fewer photons to excite the atoms of hydrogen in upper states. And that's right around 6,000 to about 7,000 Kelvin. Hydrogen is weaker, and you start to get ionized calcium lines, and they start to begin to emerge because they're the next thing that's easy to ionize. So that's interesting. And then when we get to G-type stars, which is the sun's a G-type star. The peak of the curve is now firmly in the visible range at approximately 5,500. And there's strong absorption features due to hydrogen and calcium. Well, not so much hydrogen anymore, but we have singly ionized calcium, and then some other metals start to dominate. Metals here being anything other than hydrogen the lines, or helium. But we start to see that that mostly important is the peak is in the middle of the visible spectrum. We see K stars even further over into the red side of the spectrum. And finally, we get to the M stars, which are extraordinarily cool. They peak way out in the infrared, much past the visible wavelengths. They peak out so far in the infrared that they start to peak around 10,000 angstroms or so. And then they kind of cool off. And some of the late type M stars even peak much further. When we get to the L-type stars, there's practically no emission in visible light, and you have to actually look for them in infrared, and you see lots of molecular absorption. You see there's almost no emission anymore, no absorption due to very strongly bound atoms such as titanium oxide and vanadium oxide, and these things are very, very cool stars. And if we go to the T-dwarf stars or the brown dwarfs, you see molecular absorption due to water, due to methane, due to ammonia. These things are like Jupiter's. That's exactly what they are. So these are the failed stars. They have very loosely bound molecules that can easily be destroyed if the star was hotter, but they're not, so you have a T-dwarf star. And so this is boundary zone, and they're very interesting to study because where do stars end and planets begin? That's an interesting question for astronomy. All right, so as we see, the stellar spectra are an incredibly important element of all of this. And as we look at the types of stars that we have in the sky, we can classify them to this stack of groups. And the stack of groups ranges from the hot O stars to the cool M stars. And as we look at them, we understand the nature of their atmospheres, we understand the nature of their temperatures, and we get to begin the physics of stars. And that's what we'll pick up next time. See you soon. Hello everyone, this is Jason Kendall with the next of my introductory astronomy lectures. Well, we went through the sun, then we looked at the different kinds of stars, looking at their stellar spectra, and determined that stars have spectra, meaning they can be classified according to the appearance of their spectrum. Now that's very, very, very important in terms of what makes up a star, what makes up the atmosphere of the star. But really when we look in the night sky, there's something else we want to link into it, and that is the motions of the stars themselves in the sky. Now, we're not going to really go into deep motion about the constellations and the rising sun of that. We're going to assume that we can see any star that we want at any time. And so let's pretend we're out in space or something. We're going to look at the motions of the stars with respect to each other, which is a very interesting way of looking at things. The funny thing is that to your naked eye, to the sky that you see above you, the stars seem to be fixed, but there's no real reason to think that that's actually the case. The stars themselves are not fixed in the sky. They're objects that float in space. They move in space. They're constantly in motion. But they're so incredibly far that we actually do not see any kind of motions during your lifetime, or mine, or anybody else's. You have to wait hundreds of years before most of the stars' motions can be seen. So let's look at the next thing. So let's go back a bit and say, well, how far we are. And so we're going to go back and take a look at parallax. Parallax is a way of getting distances to stars. So you have some sort of baseline where two people looking at it, two little emoji smiley faces, and you want to get the distance across, say, this river. And there's a tree on the far side of the river. So you set up a baseline, you look at somebody that's straight across. The angle between one is a right angle, that's what that little square means, and the little theta is the angle that's being measured given the baseline. And so if you know, you can use simple 8th grade geometry to learn that the tangent of that angle theta times the baseline equals the distance across the river to the tree from the smiley-faced emoji guy. We can use this to our advantage if we can figure out a convenient baseline. Because if you think about it, the smiling emoji guy sees the tree from one vantage point, and the not-so-smiley emoji guy sees the tree at a different vantage point with respect to the things behind the tree. So that's what we're really going to look at. So stellar parallax, or the parallax of the stars, means that as the Earth goes around the sun year to year, some stars appear to move back and forth in the sky with respect to background stars. And here we can see an example of 4 of them moving back and forth if you look really carefully. And so the nearer the star, the greater the movement. Stars that are nearby, let's say we got so now I'll explain this diagram. On the left-hand side, there are a whole bunch of really distant stars. We have the sun as a yellow dot on the right-hand side, and the Earth going around the sun in its orbit around the sun. And yes, the Earth does actually orbit the sun, and yes, it's actually a sphere. Jeez. Anyway, so let's pretend that the blue star that's kind of halfway in the middle is an intermediate distance star. So what we're going to do is, from our vantage point on Earth, look at the star and see where it is with respect to the background golden stars. All right, so a few months later, it's over here, and a few months later, it's over there. And then when it's there, maybe we can see it if we're very lucky to see it on the other side of the sun. Maybe we're using radio telescopes. We don't worry about it because maybe it's a radio star or something like that. So a near star will have a big wag, and it'll move a lot with respect to those background stars. Now, something a little further, the change will be a lot less. We can see that the star is moving less with respect to these background stars. And now a very distant star barely seems to move at all with respect to the background stars. And so the great shift between the near star has a really big shift, a big total angular shift in the sky with respect to the large stars, the distant stars. And a medium star has less of a shift, and a really far star has little or no shift. Right, so we can combine them over together, we can overlay them together, and then we snip out the distances to make it a little clearer, and then we cut it in half, and we define the parallax to be half of the total shift over the course of a year. That's the definition of parallax. Not the full shift, but half of the total shift. So you get a nice triangle out of it, a nice right triangle with the sun at the center. And we can then define the distance to the star in terms of the distance from the Earth. So now the baseline is between the sun and the Earth. We could have replaced the smiling emoji for the tree thing. And now the previous slide where we showed the tree, that's where the star is. And the angle is now the parallactic angle, which is the apparent shift as the Earth goes around the sun. And so the tangent of the angle of that little parallactic angle is equal to 1 astronomical unit divided by the distance to the star. That is the definition of the tangent. So what's an astronomical unit? Well, that is the average distance between the Earth and the sun. So let's take again a look at that. And so we can redefine the distance to the star, meaning 1 AU divided by the tangent of the angle P. We're going to play with this definition a little bit just to make it actually really convenient to do. What is an astronomical unit? If you don't know this, you don't know the distances to the stars. So how do we get that? We can use Venus to our assistance, because look at this, at the Venus right there, it's at quarter phase, which means we see 1/4 of Venus. That means it's at a 90 degrees if you were on Venus. The Earth, if you were on Venus, looking in the sky, you would see the sun and the Earth at 90 degrees in the sky. So therefore, the position of Venus in the sky with respect to the Earth and sun is at a 90-degree angle. So we get this nice little thing, and we can determine the distance from Earth to Venus using radio telescopes such as MIT's Millstone Hill. And you can bounce radar beams off of Venus as it's moving and determine the distance of Venus, and then use triangles, just again using triangles to determine the astronomical unit. And so all you have to do is measure the angle between the Earth, between the sun and Venus when it's at quarter phase, get that distance of the yellow line, which is the angular distance, and they'll give you the red line, which is the astronomical unit. So the angle theta is what we're trying to measure in the sky, meaning the position of the sun and Venus in the sky. And then we bounce radar off of Venus to get the distance to the yellow, and that gives us the astronomical unit. In so doing, we've learned that the astronomical unit is, by definition, 150 million kilometers, or 93 million miles. And it takes light 8.5 minutes to go that far. And this distance definition gets us out to the planets. It allows us to find the distances of planets. It allows us to find the distances to far stars. We use the AU and find out, well, how far is a parallax? Well, 1 astronomical unit is about 150 million kilometers, but stars are really small. So that angle is really, really small. And if we measure that angle in arc seconds, we find that the distance to a star that has a parallax of 1 arc second has a distance of 1 parsec. So we're defining a unit based on a fundamental measurement. If it has a parallax of 1 arc second, and we're on the Earth, and we're looking for parallax from the Earth, then the distance is by definition 1 parsec, which means a parallax of 1 arc second. That's what parsec stands for. That's equivalent to 206,000, roughly 265 AU, 3¼ light years, or 31 trillion miles, which is a long way. 31 trillion kilometers, I should say. So it's an incredibly great distance out to the stars. So the typical distance is enormous, and stars are on the order of about a parsec apart. That's how far apart they are relative to each other. So that's the definition of a parsec and what a parsec is and what parallax is. And that motion is seen in stars. And some stars have large parallaxes if they're really close, and small parallaxes if they're really far. And we discussed that in an earlier video. So the star Sirius has a pretty large parallax. It's almost an arcsecond. It's like a half an arcsecond or so. It's about 7 light years away. Now, parallax is due to the motion of the Earth around the sun, but then there's an actual motion that's called proper motion, and that's the apparent angular motion of the star across the sky with respect to more distant stars because the star is moving through space. So proper motions are really small. They're on the order of 0.1 arcseconds per year, so they really take a long time to move. That's a very, very, very tiny proper motion. The largest one is Barnard star, which really cooks across the sky. If it's going 10 arcseconds per year, that's 1 arcsecond per every 6 years. And you can multiply that by 60, and it goes a degree in basically a person's lifetime almost. And that's Barnard star. The Hyades is a star cluster. And the Hyades is incredibly important because it's a star cluster, and its proper motion is pretty small. It's less than about 0.1 arcseconds per year, but it's very close. And because of that, we actually use proper motion studies to actually find the distance of the Hyades. And what we can do is we can trace the celestial sphere. Remember the old celestial sphere where we think of the sky as a dome over our head, and then we put a grid on top of that dome and we look at the sky, and that helps us understand what's in the sky. Let's look first at a very interesting guy's work, a guy named Jack Schmidling, who likes photographing Barnard star in the sky. So he's been doing it for a long time. One of his first photos is in 1950, then in 1997, 98. He took these pictures and put them on his website, which is schmidling.com/barnard.htm. So you can go take a look at his website to see what's been doing. But taking pictures of Barnard star is kind of interesting. It's a relatively dim star, but you can pick it out. I mean, it's something you can pick out, not necessarily with binoculars, but with a relatively decent telescope. An amateur telescope certainly can pick it out. Not a 4-inch, but more like an 8 or 10-inch scope can pick it out. Because it's a really dim star. Actually, no, I think it's like a 12-inch scope you need because it's a fairly dim star. But it's bright, it's close, and it's moving fast. And it is the fastest moving star across the sky, meaning across the celestial sphere. There might be stars with higher actual velocities, but from our vantage point on the Earth, it has the fastest proper motion across the sky. All right, so it's a faint red dwarf, and it'll move the width of the moon in about 200 years, which is really quite a large distance. Remember, the moon is about a half a degree across, so it'll move the 1 degree or the width of your thumb in about 400 years. That's a very, very, very big proper motion. Anyway, go check out Jack Schmidling's website. He has a lot of fun pictures there. Another thing we can look at is that proper motion is really significant with respect to, say, 61 Cygni. It also is one of the fastest proper motion stars, and it's also a binary star. So 61 Cygni is interesting that you can actually see it change with respect year to year. And now we see this overlaid set of pictures. This is by a particular observer who posted his stuff on Wikipedia. And so go take a look at it. It's really cool. The radial velocity means it's also coming towards us. Oh, wait a second now. It's moving about 3 arcseconds a year, which is about a third that of Barnard's star. And the radial velocity, meaning how fast it's coming towards us or away from us, is measured to be pretty fast, about 66 kilometers per second towards us. And its parallax is about a third of an arcsecond, which means it's about 3 parsecs away. Remember, a distance of 1 parsec has a parallax of 1 arcsecond. So if it's a quarter of an arcsecond, this is just a little bit bigger then it would be 4 parsecs. If it's about a third of an arcsecond, then it would be about 3 parsecs. So this is roughly just a little bit less than 4 parsecs away. And it's the first object for which parallax was ever measured in 1838 by William Bessel. It's really interesting. So that's a double star. But the really most powerful one that we'll ever talk about, and we're going to come back to this when we talk about the nature of stars and star clusters and why they're so incredibly important, is the proper motion of the star cluster Hyades. And you can see it here. It's all this in the center of this image. You see a series of bright stars. It's kind of brighter than the background area, not in the center, not the little cluster that's very distant off in the upper left, but the thing that's centered around Aldebaran, which is the red star that's in Taurus the Bull. But you kind of see a V sort of shape. That's the head of Taurus the Bull. In fact, the head of Taurus the Bull in the sky is the Hyades. So it's a group of stars, and they all seem to be pretty bright. And in this particular image, you can see that the circles of the stars have gotten greater exposure on the image or the CCD or photographic plate because they're brighter. That's the Hyades in the center of this image. And as we can then say, what is the proper motion of the Hyades? We can say, how are they moving through space? We can track the individual proper motions through time of particular stars. And we find that if it's in a cluster, they all tend to move in a similar direction. Now, what's funny is that you'll notice that this particular cluster seems to be aiming towards a point. Like you can almost imagine that some of the ones at the bottom of the image are kind of pointed up and some of the ones at the top of the image are kind of pointed down. And that is because of the relative motion of the entire cluster with respect to the sun. And that angle opening, how big that kind of wedge sort of shape is, determines the distance. The farther away it is, the wider the wedge. And so narrow, close by stars have very large proper motions. But you can see that pretty much all of the stars in this cluster have roughly the same proper motion magnitude, meaning the length of the little line going either down to the left, or up and to the left. And the dots are the stars, but the little lines show where it will be in 1 year in terms of milli-arc seconds. So that's what that graph means. It's how many milli-arc seconds it's going in 1 year. So this is 0.05 arc seconds per year. So it's not a big proper motion. So that's the length of the little line. So you can see that it still is there. It's enough to be measurable. And so this is a piece of work by in Icarus in 1991. Proper motions themselves are cumulative, meaning if you wait, they'll move. And so all you have to do to find something is take images over the course of time. This is different than parallax, which kind of wags back and forth because of the Earth's motion around the sun. Proper motions, they keep moving, they move in their own way, and as they move with respect to the distant background objects, such as extraordinarily distant things like galaxies and quasars, they will be, then you can just compare images and see what's been moving. So if it's got a 0.1 arc second per year motion, which is a pretty nearby star, then it'll move almost a full arc second in a decade. And an arc second is a typical angle that you would think of as a parallax, or the boundary angle for parallax. No star has a parallax bigger than 1 arc second. Basically, because there are 60 arc seconds in 1 arc minute and 60 arc minutes in 1 degree, and your thumb held at arm's length is 1 degree, therefore, all you have to do to know how big an arc second is make 60 little marks across your thumbnail, hold it at arm's length, and then take 2 of those marks that you wrote so carefully across the back of your thumbnail and put 60 marks in between each of those. So you'd have 3,600 little lines across your thumbnail that are not crisscrossed, but are just just lines across. And the width between those lines held at arm's length will be 1 arc second. It's not a very, very big angle at all. It's an extraordinarily tiny angle. Proper motions are extraordinarily difficult to see, and it takes a long time for anything to be noticed over the course of visual observations. You literally have to wait centuries tens of centuries, or for people to actually see them by eye. So when we look now, let's take an example of, say, the Big Dipper. The Big Dipper is pretty close. So the stars of Ursa Major are pretty close. They're part of a moving group, as we call them. and they change slowly, but they take time to effect their change. But what we're going to do now is I went into this program called Stellarium, and I went over the course of 200,000 years to see how the Big Dipper will change over the course of 200,000 years. Now here we go. Some move in different directions, but the 5 and the Dipper roughly have common motions, but stars move around. So let's start today, or at least back in July of 2017, and we see the Big Dipper with Alkaid, Mizar, Alioth, Fad, Merak, and Dubhe, and centered on Megrez. And so we'll jump ahead 24,000 years, and we see that things have moved. Now there's a bit of rotation, and that rotation has occurred because of the precession of the Earth's axis around the sky. But you can see that I'm just going to wag back and forth a little bit on it, and we can see that the shape of the handle of the Big Dipper has steepened, and the box of the Dipper itself has squished a little bit, and Dubhe has moved away a little bit further. Now let's jump another 20,000 years in the future, and Alkaid scutches in just a little bit closer. Dubhe moves a little bit further. Fad gets caught up to by the others, and now the Big Dipper is starting to look a little different in 50,000 years. And as we can go back and forth, we see that it's just kind of cycle back and forth across 50,000 years of time. That actually the Big Dipper will change its appearance over time. If you went back to the time during the last ice age, which was 15,000 years ago, the stars in the sky would look different. They would have different shapes. You wouldn't recognize immediately the constellations, and you might even notice that there's some slight differences to them, which is really fascinating. Now we're going to move on and look at the nature of proper motion itself. So proper motion depends on the distance to the star. And so the closer the star, the greater the proper motion. So both of these two stars are on the blue line, and then we're going to let them move through sky, and they have the same speed lateral to, say, the sun. So the sun is the yellow dot over there. So we're orbiting the sun. So basically, we're just thinking of ourselves as near the sun. That's good enough for our purposes. And if they're both scooting by the sun at the same speed, that's what the red and green arrows mean, is that they're moving at the same speed, then the angle that they appear to move is less for the far star, the green line, than it is for the red star, the near line. So you can see there's a bigger angle, but they're moving at the same speed. So proper motion is an angular change, not a velocity, not a speed. It is an angular change per year, not a kilometers per second year, because we can see they're different distances, same speed, but different angular change depending on the distance. But let's say it's moving the same speed as the green star and the red star are moving the same speed, but if the red star is moving directly towards us, we're not going to see any proper motion at all. So that'll be kind of weird, but it has the same speed as the other one, but it's moving towards us, so no proper motion. Basically then, the radial velocity tells us what we need to know. The radial velocity is how fast it's moving towards us or away from us, and we get that from the spectrum. Remember last time we talked about the nature of stellar spectra, and we saw hydrogen lines, calcium lines, all sorts of things, but specifically hydrogen is the most prominent in most stars' lines. But if they're cooler stars, you're looking for molecular lines and so on. So if you're looking at Barnard's star, you'd be looking at molecular lines in this cool red dwarf. Anyway, as a star moves towards you, it'll be blue shifted, meaning the absorption lines in the spectrum of the star will all be shifted to a shorter wavelength. The entire spectrum will be shifted to a shorter wavelength, and that means it's called a blue shift. If it's moving away from us, then all of the spectral lines and every aspect of the star, all of the light, every photon, every particle of light will have its wavelength lengthened because of that. And so the appearance of these spectral lines will be moved to the red. So if it's moving towards us, the spectral lines move to the blue. If it was moving away from us, towards the red. And if it's moving across our line of sight, we don't see any change at all. So we could have 3 exactly identical stars, meaning their spectra would look exactly identical. But if you put them side by side, one of them would be red shifted, one would be blue shifted, and one would have no shift, so they'd be in the middle. That'd be interesting, but they're exactly the same spectra, and the only difference is how fast they're going towards us or away from us, and that's called radial velocity, and that is a speed. So how much of the speed is towards us is important. Here we just looked at left or right and across, but what about the angles in between? This is what we mean. There's the spectrum of the star. They get noticeably bumped. And there you can see the absorption lines of, say, oxygen and hydrogen. Specifically, this is an A-type star. And A-type stars have incredibly deep, the most prominent hydrogen lines of all. So if it's convenient A star, then it's great. But because it's easy to find hydrogen lines, you know what you're looking for. So like hydrogen beta, that is that particular wavelength, and there's 6563 angstroms. There's a hydrogen alpha. Here we have the Balmer transition lines and so forth. The spectrum of the star, the entire spectrum will be shifted to the right, meaning longer wavelength, bigger wavelength, bigger numbers, but the shape will remain exactly the same. If it's blue shifted, on this graph, it would be shifted to the left. Everything would remain the same, except everything would be shoved to the left. And that's what we mean by redshift or blue shift. It will be pushed to the left, or the entire spectrum will be pushed to the right. And that is called redshift. And that is dependent on the speed with which it's approaching us or retreating from us. So now we're going to get to an important element, which is called true space motion. Where is the star actually going? To find the actual space velocity, how far it's going, how fast it's going in, say, kilometers per second, not just an angle, but in kilometers per second, we need to have measured the proper motion, which means we got to watch it for a few decades to see if it actually moves. Then we need to know the distance in parsecs, which we would get by looking at the parallax, if it has one. And then we would look at the radial velocity, which is the redshift or blue shift of the lines according to the spectrum. And so the transverse velocity is the actual speed across the line of sight, and the radial velocity is measurable from the distance and the proper motion. And the radial velocity is because of towards us or away from us. You add these two arrows, the green and blue arrow, together, meaning take the green arrow and put the tail of the green arrow at the tip of the blue arrow. And you see that it could fall right on that black dotted line. And it would then say, if you add the blue arrow and the green arrow together, you would get the red arrow. That's called vector addition, but it's interesting to think. And we can formalize that by saying, well, let's actually take it one step at a time. But the tangential velocity, v sub tan, would be some crazy number, 4.74 times the proper motion in arc seconds per year and the distance in parsecs, and that gives you kilometers per second. And where that 4.74 arises because you're using arc seconds, years, and parsecs as your units, and that 4.74 converts that when you multiply those two numbers together into kilometers per second. So that's where the tangential velocity comes from. Then what you do is you square that, take the tangential velocity, square it, and add it to the square of the radial velocity, and then take the square root. And that's the length of and take the square root of that, and that's the length of the arrow. So you can use Pythagoras' theorem just like you can with the lengths of arrows, in the same way that you can do with just lines. So we add the arrows together. How long is the true space velocity, v sub space? It depends on the square of the radial velocity plus the square of the tangential velocity, square rooted, you get the true space velocity, and how fast it's really going through space and in what direction. It's really interesting. Why would we bother even doing all this? Because that sounds like a heck of a lot of work, because that's called astrometry, and it is a heck of a lot of work. We gotta wait decades to do it. There's other things to do, like surf the internet and look at Instagram pictures of cats. So when we do that, we'll find that it's incredibly useful for astronomy, because when we can find how the sun is moving through space. And it seems to be moving towards the constellation of Hercules. We can then also take large-scale measurements of many stars around us and find out exactly how on average, all the stars are going around us. And we find that, in general, everybody's kind of moving in a plane around the galaxy. And so the galactic plane can be measured by looking at space motions as we go around the galaxy. And that can actually tell us how fast we're moving around the galaxy, as well as everything in the sky around us. Finally, we can find really, really, really strange looking stars. And those strange stars might be moving in some very weird way because they got lost in space, or they're not lost in space like Robinson Crusoe and the robot,
but they might be coming from a very strange location, maybe the halo of the Milky Way, or maybe they're part of some other group, some other strange kind of star. The amazing thing is that measurements of stellar motions is what actually helped us to discover the existence of dark matter. So simply taking pictures of the stars over the course of decades and seeing how stars move through the sky and therefore how we move through the sky, and then looking at that with respect to Newton's laws of gravity, we then can discover that there's a whole bunch of things that we do not see. And that thing we do not see is dark matter, because everything is moving a little too fast for what it should be. And that gives us a really interesting thing. So we link the nature of just pictures of stars moving through space, and that gives us an insight into the nature of physics and the nature of matter itself, which is really a fascinating integration. So that's what we mean by the motions of the stars, and all the stars have different kinds of motions, from parallax to risings and settings, and the diurnal motion, to annual motions, to the proper motion across the sky, and tangential velocities across. And all of those things actually have great meaning, because none of those stars that you see on a starry sky are actually fixed in space. They're moving too, which is a really fascinating thing to think about. All right, thanks again, and we'll see you soon. Hello everyone, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Last time we were looking at proper motion, the motion of the stars through the sky that's not dependent upon the Earth's motion around the sun, and that's what we call proper motion. But there's other really interesting things that we get from straight up amateur observing of the sky. If you actually look out with a small telescope or binoculars, you find one of the more interesting little wonders of the night sky is that sometimes two really bright stars are very close together as seen through binoculars. But in the sky, they look like one star, but together, when you look at it through binoculars, you can resolve the two stars, and they're called binary stars. So binary stars are a really interesting set of things, and they're subject of massive amounts of study and research, because they can tell us a huge amount about the nature of stars. And by the way, they're really pretty to look at. So if you get a chance to go to some amateur club or something like that, or get out in the deep woods or something, take a pair of binoculars or a small telescope and go take a look at some of the prominent binary stars in the sky. One of them is Alcor and Mizar. And Alcor and Mizar are the middle star in the handle of the Big Dipper. And if you look really closely at Alcor and Mizar, you can see that one of them is pretty dim and one of them is really bright. And that's a classic visual binary. And if you look closely at Mizar, which is the bright one in this image, which has been derived from the Palomar Sky Survey, then you'll actually see that Mizar is actually a binary itself. And so when you look at it in a small telescope, you actually see that. But in this image, they're too close together, they get washed out, and you can't see it. Anyway, so apparent binary stars are stars that just happen to be in the same direction. And sometimes they can be very distant, very far apart. Another other beautiful pairs of apparent binaries, such as Nu Draconis. And I believe Nu Draconis is a beautiful actual binary, but this is definitely one of the prettier binaries in the sky. This was taken by David Ritter, and I believe this is also from Wikipedia, but David Ritter took this great photo of this wonderful binary. And sometimes these are called the cat eyes, because if you look at it through a telescope, there's pretty much not many other really bright stars in the field. And so they look like little eyes staring right back at you. And that's called Nu Draconis, one of the nice binary stars of the sky. One of the classics of all of the stars of the sky, all of the binaries, are true binary stars, such as Albireo. Albireo is Beta Cygnus, and it's halfway between Vega and Altair in the sky, right along the Milky Way. And that's why there's so many stars in this image, is because from the Palomar Sky Survey, we see that since we're looking along the Milky Way, we see a huge number of stars in the middle. And that's something you can see if you go somewhere dark. But Albireo is really wonderful because you get a really gold star right next to a really blue star. And as we look out in the sky, we find that a lot of stars are actually, it's pretty common for them to come in binaries. And then when they're orbiting, when they're true binaries, not just apparent binaries, but if they're truly binary stars, then they actually orbit each other. They orbit a common center of mass, meaning then one star doesn't just orbit the other like the Earth orbits the sun. No, both of them have such a great enough mass that the center of that mass, the balance point between the two of them, is not inside either star, but maybe halfway between or 3/4 to the way out for one, depending on the masses. But about 60 to 70% of all the stars in the entire sky are actually two or more stars. So most stars are binaries, which is really interesting. So when you look out into the sky and you see all these stars, most of them are binaries, which is pretty cool. And another great example of a binary star that you can see very easily is the brightest star in the sky, Sirius, Alpha Canis Majoris. And Sirius has a very, very, very dim companion. It can only be seen with large telescopes, and it's very close to the star. In fact, this image for the Palomar Sky Survey, it's actually too bright. It's washed out its companion star, so you don't actually see the companion star in it. But let's take a closer look at this particular true binary star. True binary stars are gravitationally bound, and the gravity between them will determine how they move. And so this is yet another aspect of the motion of the stars. So proper motion is the motion across the sky, but then there's an effect of the space motion as it moves. Maybe in addition to proper motion, you actually see the stars actually orbiting each other. And if you could actually orbit each other, then you could measure, then you know they're at the same distance. So then if they're orbiting each other, they're at the same distance, you can figure out how far apart they are. If you can figure out how far apart they are and actually get their orbit, well, then you can use Newton's law to determine their masses. So now this is telling you about the physics of the stars themselves. All right, so the types of binaries that you actually see that are actual true binaries, not apparent binaries, but true binaries come in three basic classes. One is a visual binary. You can see both stars and follow their orbits with time. And so a visual binary is definitively something you can get inside a telescope. And you can make both stars out. And Sirius is one of the most important examples of such binaries. Eclipsing binaries are interesting. They're so close together that we can't see them as separate stars. But interestingly enough, if you watch their brightness over a period of time, you'll actually see them get brighter and dimmer when one star goes in front of the other and blocks some of its light. And when that happens, you get an eclipse. And if that eclipse is strictly dependent upon the location of the star in the sky, and that eclipsing binary star then dims in a particular way. And that's the classic example is Algol, or Beta Perseus, is one of the classic examples of that. That's been known since antiquity. That's why it's called Algol, which means the winking demon. So even the ancient Greeks knew that Algol was a blinking star. And finally, what you have is a spectroscopic binary. They're too close, again, just like eclipsing binary, to be seen as separate stars. But you can detect their orbit by looking at Doppler shifts of their spectral lines, and Gamma Cassiopeia is an example of that. All right, so let's go back to Sirius. What's fascinating is that people have been watching Sirius through telescopes for a long time, and so for about 100 years, people have noticed that Sirius A, which is the bright star, and Sirius B move together through the sky. And Sirius A doesn't move as much as Sirius B. And Sirius B is a white dwarf star. And Sirius A is, I believe, an A-type star. And they're all very, it's a much brighter, much more massive star than the white dwarf that orbits it. And notice they have these funny kind of circular orbits. They orbit a center of mass, which is at the center of this diagram. So you got this kind of plus sort of shape, which shows where the center of mass is, where the two straight lines converge. And the orbits of the stars orbit that common center of mass. And the reason it doesn't look centered up to us is because the orbits are inclined with respect to our viewing of them. So they don't match up that, but that's exactly where the center of mass actually is. So they orbit that center of mass. So when one star is far, the other star is far, and when they're near, they're near. So they trace the same location in this. They go from the outer portion when they're very far apart to going very close together. So they go far to no close to far to close. All right. So what I did is I decided to use a nice little tool called Sky Safari to actually show you the orbit. So now unfortunately, Sky Safari centers on a particular star. So what I'm doing is I'm actually just showing you the orbit of Sirius B, the white dwarf, with respect to Sirius A, the bright star in the sky. So you have Sirius A there, and we see over time, as you look at the time that's passing on this thing, we're now almost 100 years in the future, and so it orbits quite quick. It takes a long time for it to orbit each other, and we can see there they go orbiting, orbiting, and orbiting. But as we zoom out and look at larger and larger areas of the sky, we see that once your field of view is typical for a large telescope, or with a standard eyepiece, which is about what we're looking at now, it's hard to make out the binary pair. Okay, so now what we can do is we can go faster in time, actually turn off the double star, and we'll just see exactly how Sirius moves in the sky. Last time we talked about proper motion, so now let's actually show what that looks like. So the grid I'm turning on here is the coordinate of equatorial coordinates, which is with respect to the Earth's equator and the North Celestial Pole. So that was a little bit busy, so I turned it off. And now what I did is zooming out to show you the proper motion of Sirius. Now what I'm going to do is actually go much faster in time and see how we look. So we'll zoom in a bit more, I'm not really sure what I'm doing here. Okay, let's go click around here. Let's find out the constellations, because now if we check out the constellations and look at the boundary lines of the constellations and the traditional lines that we see in the constellations themselves will change over time. And this is too busy, so I'm just going to dim some of the stars so we only get magnitudes down to 6, which is typical for like a really, really, really dark location. So magnitude 5, which is not so dark. Now I'm going to actually speed up time again. And as I speed up time, I'm going to change it from 24 years to time. Now we get the effect of all of the changes of proper motion. We can see the years going by rather rapidly. We'll turn off the planet so we can actually see what's going on. And you can see the years are now 14,000 years in the future, 15, 16,000, 17,000, 18,000. And we can see the proper motion of Sirius across the sky with respect to all the stars in its background. And that's because Sirius is quite near to us, only about 7 or 8 light years away. And as such, it moves quite along really quickly, just like Procyon does. It's sneaking into the picture over there. So that gives us a little bit more about the nature of all these stars and their positions in the sky, and specifically one of the most important binaries, Sirius A and Sirius B. So we can then reduce the motion and then make a graph out of what we see. And we reduce it so that we only worry about the motion of Sirius B with respect to Sirius A. And so we center it up, and we see that it takes on the order, what do we got there? Approximately 1991 all the way through, oh my goodness, 1969, 73, 60. Takes about 50 years for it to go around in one orbit. And that orbital time frame is about 20 or 30 arc seconds across. So you do have to have a very high resolution in order to see them and split them. But if you have a large telescope and you're using, say, a 17 millimeter eyepiece or a 12 millimeter eyepiece, you should be able to split the two stars. But Sirius B is very, very dim compared to Sirius A. But this is called a visual binary. So you can actually track them, which allows you to actually use Newton's gravitational law at Newton's laws of mechanics to actually get the masses of both stars. Measuring mass is really important because mass is one of the most fundamental measurements we can make of anything. And so mass determines gravity and the gravitational pull on it, and it determines your weight, how much mass you have determines your weight on Earth. And so the Earth's mass can be determined by the motion of the moon or by satellites in orbit. And the sun's mass is derived from the motions of the planets. And all other stars' masses are based on the fundamental fact that you have to see their effects on companion stars. So if you take stars like Sirius, you can hopefully derive something from Sirius A and understand that kind of star, and then apply what you know to other kinds of stars. So the only kind of star that you can actually get that derives directly their masses is from visual binaries. All the rest are much more difficult. Visual binaries are the most important, and they're usually near enough. You can get parallaxes, and then if you can get that, you can get a real physical separation, And that gives you exactly what you're looking for, which is a map or a catalog of stars of known masses. And so the Washington Double Star Database, which is maintained by the Navy, the U.S. Navy, which is really interesting that they do that, maintains a massive database of double stars. And all sorts of data points are given by various researchers, and they maintain this database to try to see what's going on. So here's an example of one of them, and its label is there, WDS 1805 2334. Well, that would be something you would see in the database. And so this is a well-made map of a binary star. How do you get the mass? So if you have them, you can think of it as balancing on a little teeter-totter. So put that little black triangle in the middle, and so there's separation. If you can get their physical separation and determine their center of mass, then the ratio of the masses equals the inverse ratio of their distances from the center of mass. And the distance between them is the sum of just the two of them. So we've got this A, the total A is the distance between the two stars, M sub 1, star 1, and M sub 2, star 2. And A1 and A2 are simply the distances to the center of mass, which is the fulcrum point. So you can just imagine that they'd be perfectly balanced on a big, 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 long stick like that. So the fat one has to be close to the center, and the little one has to be far away in order to balance it. So that's where you have the ratio of the masses is equal to the inverse ratio of their distances from the center of mass. So if you can determine their distances, their absolute distance, and determine where the center of mass is, then you have the ratio of the masses. You know how, and that's a very easy calculation because that's just distance. That's their distances. How do you get distance? You need to have parallax. If you have parallax, you can get their relative distance between them. So now you have the ratio of the masses. How do you get the individual masses of stars? Well, it gets tricky. If you measure the period of the motion, and then you measure the semi-major axis, which is how far apart they are at the greatest distance, or their average distance between them, and then you can solve Newton's form of Kepler's third law to get the sum of the masses. So you can look at their separations and get the ratio of the masses, and then you can solve this equation to get the sum of the masses. And if you have a ratio and a sum, you've got two equations and two unknowns, and so there you go. You can solve for the individual masses. But you have to accurately measure the period of the rotation, you have to accurately measure their distance between each other, and you have to accurately measure where the center of mass is. And once you get that, then you can get the individual masses of stars. And that means you got to take up a lot of time, and it's a huge amount, and you have to know the distance. If you do not know the distance to the star, then the distance between the stars will be a mess. So a little tiny distance error makes a massive error in the mass. So you got to be really, really careful. And so getting the actual distance in terms of the astrometric distance with parallax is critical. So parallax distances are incredibly important for all of astronomy and the physics of stars. And it all begins with these visual binaries. So the massive Sirius B, which is now visualized in this Hubble Space Telescope image, is being shown here. And Sirius B is a little tiny star. It's known to be about 12,000 kilometers, or a little bit smaller than the Earth. And it's a little tiny thing. And so we have Sirius A, which is really, 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 really bright in the center of the field. And then there's this little tiny dot to the lower left, halfway down at about 8 o'clock on this image of the Hubble Space Telescope. And this Hubble image shows, there it is. And so it's a little tiny thing, and it's a very, very small radius star. And we'll get to how we get the radius later. But we've learned that the mass is about the same as the sun. But the size of that star is a little bit smaller than the Earth. And you can actually where the Hubble Space Telescope did is they looked at the redshift of light coming off of the white dwarf. And this is what is called a white dwarf type star. And the redshift of the light coming off of there is gravitationally shifted, as we saw in one of my earlier videos, that gravitational redshift can occur, and it's the loss of energy of light as it comes from the surface of something, even the Earth or the sun. But with a white dwarf, it's measurable. And so we can actually measure using the redshift of the light coming off of the white dwarf that it has just about the mass of the sun, but the size of the Earth. So it's an incredibly tiny, massive object. So spectroscopic binaries, but most binaries are really just too far away to see stars separately. That's unfortunate, but we don't have a lot of close stars, but if we did, we'd probably have problems of a different kind. We have comets falling in and dinosaurs being killed all over and over again and so forth. And there's all sorts of stuff about that. But in any event, you can detect the orbital motion of stars by looking at the Doppler shifts, the periodic Doppler shift of the spectral lines of the stars themselves. And that tells you from the Doppler shifts, that can give you the period, the orbital period, and it can give you a rough guesstimate of this and give you a size and the pattern of the orbital velocities. So if one of them's moving, if one of the sets of lines is moving small, then it's not being shifted as much. That would be star A in this diagram. And star B, however, would have a big shift. And so that big shift would mean that it's a less massive star. And the ratio of how much they're changing is the ratio of their masses. So since you can't see them, you must estimate the semi-major axis from the orbital parameters derived from the spectral Doppler shifts. And the real problem is you can't tell if the orbit is tilted like you can with, say, Sirius. So again, you have to know the distance in order to get the semi-major axis estimation. All you can get is the semi-major axis with a little bit of inclination. So that's one way to get really close to getting masses with the spectroscopic binaries. And the shift is more detailed here. We can see that one of the stars is shifted left and one of them is shifted right. And sometimes you only see one of them. Maybe one star is simply too dim in order to be seen. And so you just see it shifting back and forth and back and forth and back and forth. And that's called a single line spectroscopic binary. And that also occurs. So let's look at a real big piece of data. And this is from 2013, published by R.F. Griffin in the Astronomical Journal. And these are radial velocity measurements of an actual spectroscopic binary. So we looked at a particular wavelength of light and then saw what the radial velocity is for that particular wavelength over the course of time. And notice that it's not just back and forth, that there's a distinct curve signature. And you can use the curvature signature to determine the orbital parameters even more. This radial velocity measurement carries a huge amount of information, but the most important information that it carries is mass, because you want to be able to derive the mass of that star, because that gives you the fundamental physics of the star. And that's what we're really after in this thing is, why do we want the mass? Because that tells us something really interesting later. But the measurement actually, the interpretation of this curve such that you can get the mass of the star is a real work of art. So you can go look at his paper if you want to, and it's on archive or whatnot. I'll put a link on YouTube. So we're going to apply this to a particular star next time when we talk about the incredible discovery around the nearest star to us, which is Proxima Centauri. Proxima Centauri has been found to be a binary, but of a different kind. So Alpha Centauri is a two-component system. It also has a third component named Proxima Centauri. And we can see Proxima Centauri highlighted in this image, but they're gravitationally bound, and Proxima Centauri is the nearest star to us, other than the Sun. And it's an incredibly far location, like almost 4 light years, just under an arc second of parallax. But it is a pale red dot. And so this pale red dot becomes an incredibly important thing for us to study for a lot of reasons, which I'll get into next time. We'll see you soon. Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Last time we began the process of looking at binary stars, and this time we'll finish it off and also talk about what the implications of binary stars are. So we kind of finished off last time by talking about spectroscopic binaries, which are a special kind of binary star that only show up in the spectrum. So what happens is, in, say, the example that we're seeing here, is that it's actually 2 stars, but only one star can actually be seen at a time, because it's so much brighter than its companion that the companion only shows up as a result of the Doppler shift, the oscillatory Doppler shift of the primary star. The absorption lines that you see here get absorbed, get sent to, we have a laboratory reference, and then the starlight is shifted to the red, then it's shifted to the blue, then it's shifted back to the red. And so the star itself, the brightest star, is the only one that can be seen. And this is called a single line spectroscopic binary. Now, if you can see the lines of both, then they kind of wag back and forth, but sometimes you have such a dim star as maybe a red dwarf star compared to a G-type or an F-type star that you can only see one of them. Such as the example I gave before by R.F. Griffin, where we see only the spectroscopic data of the radial velocity, the radial velocity of the motion of one star. Specifically, the star is HD 105892 from Henry Draper Catalog, number 105,982 in the Henry Draper Catalog. And it's out of the Harvard data set. So this is a binary star. But what we see is that the radial velocity of a particular wavelength of light, and I invite you to go check out that link, and I'll also leave it on the YouTube links, is that the radial velocity associated with that goes back and forth in terms of towards us and away from us in a very, very regular pattern. And this regular pattern encodes a whole bunch of data, meaning notice how it kind of goes up really fast and then down really slow and then up really fast. That means the orbit is inclined with respect to us. It also means that there's an unseen companion. And there's a number of other important things. And the radial velocity itself, as you know, goes back and forth between it because the star system of two is actually apparently rushing away from us. So, or actually rushing towards us, it's minus. So we have a radial velocity towards us, so it actually has a negative radial velocity. So the star is roughly speaking coming towards us, but it's certainly going across our line of sight. But the radial velocity itself encodes a huge amount of information about the nature of the structure. We can determine the mass of the star that's orbiting it, or at least get an estimation, and a number of other things, as well as hopefully the orbital eccentricity and potentially even the type of star it is, by just looking at this curve. Let's look at a really important one. Last time I described that Alpha Centauri AB, which is actually a binary system in of itself, is orbited by another star, Proxima Centauri, and Proxima Centauri's orbit kind of goes all the way around the star. It goes all the way around in the course of a very, very long period of time, maybe 500,000 years or so. Well, I'm not sure the exact amount, but it's on the order of a couple 100,000 years. And so this is an image that was taken by the Digitized Sky Survey from the PAW Sky Survey. And we see there's Proxima Centauri, which is actually the nearest star to us. Proxima Centauri orbits Alpha Centauri. And right now, it's just a little bit closer to us than Alpha Centauri AB, which are two stars, and they're so close together we can't actually make them out due to this particular image, due to how bright they are. But Proxima Centauri is almost lost in the background glow of all the stars that are out there. They're deep, deep, deep when we look in the Milky Way. So all of these stars, only Proxima Centauri has a very high proper motion, as we saw last time what proper motion is. And it also has a very large parallax. It has the largest parallax of all stars, so it's the closest. When one looks at Proxima Centauri and looks specifically at the Doppler shift of that, there's a very strange thing. It's, of course, walking across the sky and slowly moving away from us, and that's what the radial velocity change over the course of 2016 showed. But there's a very, 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 very tiny radial velocity component that is not associated with the proper motion or the radial velocity around the star. But apparently there is a planet orbiting Proxima Centauri. And so this is the pale red dot group. And this was done by a group by Engelada Escudé at European Southern Observatory. And there's the link below. And I'll put a whole bunch of links associated with this. Proxima Centauri itself is approaching the Earth about 5 kilometers per hour, about the nature of a walking pace. And occasionally it actually changes with respect to up and down. So we have that we can detect the Doppler shift of the red dots are the actual data, and the blue curve is the best fit to that data. And so what we see is that the red dots indicate that there is, and the bars, those little scraggly bars going up and down, those are the error bars, or how well we know the data point inside the red circle. So it's interesting to note that when in science, you actually have to not just show your data, but you have to show how well you know your data. And so we can see that the bars are fit by the blue curve. And so the best fit blue curve to that data looks like this. And so we see that the Doppler shift seems to have an 11.2 day period. And that is due to a planet orbiting Proxima Centauri. And we'll get to know exactly how we know that in a little bit. And the star itself is a much smaller star than the sun, and the planet is a little bit bigger than the Earth. And so we can actually determine that. And I'll show you how we're going to do that in a bit. That's fascinating. So it actually would be orbiting inside the orbit of Mercury. So this planet, whatever it is really close to its star. So what do we know about this? Let's go back, and we'll eventually get back to that, but let's look at other kinds of binaries. One of the most important kind of binary stars are eclipsing binaries. Eclipsing binaries, and this is an incredibly important thing to detecting planets around other stars, which is one of the most important areas of research in current astronomy today. Eclipsing binaries are two stars orbiting each other nearly edge on to the line of sight. So we would look at them and they would appear to be wagging back and forth, much the same way if we looked at Jupiter and its moons going around. The orbit of the moons of Jupiter is roughly coplanar to the orbit of Earth around the Sun and Jupiter around the Sun. So we see that Io, Europa, Ganymede, Callisto occasionally pass behind Jupiter, and this is easily seen in a small telescope. And the star and the planets, the moons of Jupiter can be seen to pass in front of Jupiter. The analogous thing is, what if we have a star, and that star has a companion star, and the sum of the light of them is when they're brightest. And then we'll look at this little graph at the bottom. The point one is we see that both stars are visible. Nobody's eclipsing anybody. And so you get all the sum of all the light of the stars. And then if it goes in front of the star, the little star dims the big star. And so you get a big drop of brightness because it's covering up a bit of the star. Now, inherently, the little star is very dim. So it doesn't contribute much light. So then when it gets on the other side, it goes back up to level 3, which is the standard level of seeing the light from both stars. And then the little star goes behind the big star, meaning it's both little in mass and little in radius. And it's also little in terms of total luminosity. So when it gets its light blocked, it doesn't have as deep an eclipse. You see this pattern in eclipsing binaries where you have one big dip and one little dip, and then a steady amount between them. Or at least that's the pattern that you look for. And of course, nature throws you some really weird things. And the Kepler Space Telescope sees a huge number of these. And that's an amazing thing. But eclipsing binaries, by definition, are really rare because you got to get them all lined up perfectly. And so if you look at the nature of how many stars might be in binaries that actually are eclipsing, we can measure that eclipse. The two stars have to be really close. They have to be perfectly aligned. Stars aren't really that big with respect to the angle that they could actually go by their eclipses. So it's much less than 1% of all the stars, roughly about less than 1% of all stars that are binaries or eclipsing binaries. So they're really tiny. All right, so what the fun part about these is that once you know that a star is an eclipsing data, they are actually the best data of all because the periodic drop is indicative of the period of the orbit. And if you can look at the spectra, you get the speed. And once you get the speed, then you don't even know, and you don't have to know the distance because you both have the orbital speed and the periodicity, and you know the orbital inclination. And so because it's almost edge on, and since it's almost edge on, or almost perfectly edge on, you can actually determine the masses of both stars. And how that is actually done is a little bit outside the scope of an introductory lecture. So they're actually the best versions of binaries because you don't have to worry about that orbital inclination parameter. You just go right with it. So partial eclipses are harder to get if you find partials. But the neatest thing is that you can actually get the atmospheres of stars as the edges. We can see inside the diagram, the red-black diagram, that the edges are kind of sharp. But if they're softer or smoother or go down and they smoother, rather than being the sharp lines, that they're smooth, that actually would indicate partial eclipsing because of the atmosphere of either one star or the other. And that can tell you information about how extended the atmospheres of the stars are, because some of the light can pass through the atmosphere of a star. And if they're so close that they can actually be tidally distorted, that actually changes the actual shape of the curve, because maybe the stars aren't perfect spheres because they're so close that they turn into teardrops as they tidally distort towards each other. So eclipsing binaries are incredibly important for the study of binary stars, but they themselves have problems if they're too close, and then they're very interesting in of them own selves. So here's a sample of a light curve that we would see from an eclipsing binary. Stage 1, you see both. Stage 2, the little stars in front of the big star, so you get a big, 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 deep eclipse. Stage 3, you're back to seeing both. Stage 4, the little star is behind the big star, so it doesn't dim as much light because the little star doesn't emit as much light. Back to the massive amount in stage 5, and then back to the big eclipse. So this eclipse happens over and over and over again with time. And here's one of the classic examples. This is Beta Perseus, or Algol, which I discussed in the last lecture. And we're looking specifically at a wavelength that's 12,000 angstroms, or deep in the infrared. And so we can actually get a much clearer image. And so we're looking at an infrared image of Algol, or Beta Perseus. And one of the more important lines, the wavelength at a specific wavelength. And so we see, instead of having time, we actually sum up over a huge number of these events, and we combine them together, and we get what's called the phase. And the phase of it is like 0 would be the maximum depth, and 1 would be back to the maximum depth again. And this is similar to actually looking at it from an angular standpoint, or rotating around a circle. Because if it's the same system, you'll always get the same phase, back and forth and back and forth. So you should expect over a large number of observations to build up a curve like this. And that's what people have done with Algol, or Beta Perseus, the winking demon of Perseus. And it is the quintessential eclipsing binary. And it takes about 3 days for this to go through a full cycle. And I invite you to go and look it up on the web and see exactly how you can observe the minimums and maximums of it. And it actually doesn't last very long, because if it's about 3 days, then the minimum is only a few hours long. And the lesser minimum, when the smaller star passes behind the big star, is not as easy to detect, but you can actually see it naked eye. That's what's neat about Algol, is that with just binoculars, you can actually, or not even binoculars, if you know when to look and how to compare the stars, this is one of the fundamental things, and that's why the credit is for AAVSO, the American Association of Variable Star Observers, which is where this comes from. So I invite you to actually go and check out Algol on the American Association of Variable Star Observers, or just pick up Sky and Telescope or any place else where you can find an ephemeris of Algol and its minimums and maximums. The observation of binaries gets us the masses of the stars. And by combining visual binaries and eclipsing binaries, there's only a few hundred stars whose masses are determined incredibly accurately. So all other stars in the sky are actually determined on the basis of these visual binaries and eclipsing binaries, and then looking at the physics of those particular stars, extracting the information from that, and then pushing it out and looking at other stars of similar type. And what we mean by similar type is similar spectral type, like OBAF and GKM type stars, like we saw in the previous lecture. And so every star fall is determined by its spectral characteristics. So all we have to do then is say the mass of a particular star. If the star has the exact same spectrum, it must be that kind of star. So we assume the masses of the stars are related to their spectra. We haven't shown that conclusively yet, but we can actually hopefully determine that that is the case. And by looking at these events, we can see that the range of stellar masses is about 7% of the mass of the sun to about 60 or 100 times the mass of the sun. But really massive stars are insanely rare. There is a really wonderful study that people do, and that is simply to professional astronomers really are quite interested in how the stellar masses are related to their spectral type. And if we look at their stellar masses, we actually see that there's a distinct relationship between the mass of a star and its spectral type, specifically for stars that we call main sequence stars. We haven't gotten to the main sequence yet, but let's just look closely at this, and we find that we have some sort of interesting relationship between m sub v, which is the luminosity of a star, and its spectral type, OB, GF, K, M, and the very low mass L type stars, or maybe T and V get to be tossed in there if we want to talk about brown dwarfs too. But we see that there's an extraordinarily tight relationship between a mass of a star and the mass of the star compared to the sun. That's what, like, 1 is a single solar mass, 1/10 is 1/10 of a solar mass, and 10 is 10 times the mass of the sun. And if we look at close binary stars and look at them very extensively and do extensive studies of binary stars, we find that there is a distinct relationship between the mass of a star, its spectral type, and its absolute luminosity. That is critical. And the very fact that there is this relationship is insanely important for main sequence stars for astrophysics. And I'll let you kind of sit on this and think, wow, what is that? And how do we justify that? And I'll get to that. But here we have OBFGKM, which we defined 2 or 3 lectures ago. And m sub v is absolute visual magnitude. Remember, we talked about visual magnitudes very early on. And absolute visual magnitude can range from really quite faint at down to 22 to extraordinarily bright at -6. And our sun is approximately a magnitude 6, absolute magnitude 6 star. And just to remember that a difference in 5 magnitudes is 100 times in terms of brightness. So a 20th magnitude star is 100 times dimmer than a 15th magnitude star, and so on and so on. So this ranges an incredible amount of brightness from, say, -5 down to, say, +20 is 100 to the 5th power, which would be 100, 10 to the, it would be, well, 100,000. 10 to the 10th power, a billion times in brightness between the two. So the brightest of all the stars are almost a billion times brighter than the dimmest of the stars. So stellar masses can be derived from close binaries. They have a distinct relationship to the spectral type, and they have a distinct relationship with respect to their absolute magnitude, which is called which is an incredibly important thing for the future. And that mass luminosity relationship is critical to astrophysics. In this study, we find that for stars roughly below a quarter of the mass of the sun, that's about 41% of all the stars in the sky. And between about a quarter of the mass of the sun and about half the mass of the sun, that's about 28% of the mass of all the stars in the sky. And between all the stars that are half the mass of the sun to about the mass of the sun, it's about 19%. So if we add that all up, we get about 50, 60, 70, 80, and wow, that's a lot, isn't it? 60, 70, 80, 88%, almost 90% of all the stars in the sky are either the mass of the sun or less. So if you look out in the night sky, 90% of all the stars in the sky are smaller than the sun. It used to be thought that the sun was a typical star, and that's why we started with it with all our long thing about the sun. But really, stars half the mass of the sun or less are the most common types. That's fully 2/3 of all the stars in the sky. In fact, I would say it's 70%. 70% of all the stars in the sky are less than half the mass of the sun. So that's a really big chunk. And so most of them are really dim because we saw in the previous that their absolute magnitudes of low mass stars are way down here and they're much dimmer than the sun. So when we think about that, oh wait, what are the ones that are half the solar mass? Those are M-type stars. K and M-type stars make up 70 to 80% of all of the stars in the sky. And way up here in the upper left, the OBAF-GKM, those make up the tiniest fraction of the more massive stars. So the brightest of all the stars that you see in the night sky on average, are extraordinarily rare. And that's really interesting. We go to the more massive stars, but between 1 and 2 solar masses, it's about 8% of the stars in the sky. If we then think about 2 to 4 solar masses, that's 3% of all the stars in the sky. And we go up even more and more massive. such a tiny number of them are more than 20 times the mass of the sun. Less than 6/100th of 1%. So 6 out of every 10,000 stars are more massive than 20 times the mass of the sun. So they're rare. And all the bright stars that you see naked eye in the sky are mostly these bright, bright, bright stars, which is really fascinating. So I'll let you go through these review questions. You can pause this, which tells you something about the nature of all the stars in our night sky. But let's go forward. And I promised you something from the very beginning, and this is a view of the southern sky. And this is the view that was taken by the group that was looking for a planet around another star. And that planet is around Proxima Centauri. So we see the great southern sky, the Carina Nebula in the middle. We've got the Southern Cross stacked in the middle. And at the left, the yellow star is Alpha Centauri C, which is very, very close. It's almost impossible to see Alpha Centauri A, and you notice that Alpha Centauri C is actually very, very close. Well, Alpha Centauri is the bright yellow-white star, and that's actually a system of stars. But that yellow-white is the same as the sun. So one of the closest stars to the sun is a G-type star, just like the sun. Centaurus is very, very close to it, and this is the image taken by Beletsky and the group that hunted for it. And this particular image was taken of the observatory that actually made the discovery that we're about to talk about, which is Alpha Centauri A and B, which is a very, very tight star. And we see the location of Proxima in the sky with respect to it. So this is a southern hemisphere only observed thing. And Proxima B was discovered using the HARPS instrument at the European Southern Observatory's 3.6 meter scope down at La Silla Observatory in Chile. We discussed all that, so I invite you to go take a look at ESO's, European Southern Observatory's La Silla Observatory, to see how they actually did discovery and what this telescope looks like. So once again, there's the sky, and we see the Proxima Centauri is lost in there, but just for your own amusement, there it is in the lower right-hand corner. You can barely see it. If you look back and forth between them, you can almost not make out Proxima Centauri, the nearest star to us. And then we look at the star chart to see exactly where it is in the sky, and we can see it's very deep in the southern hemisphere, so it can't be seen from New York City, where I live. And it can't be seen from most of North America. In fact, it's so far south, you got to be below the equator to see it. It's unfortunate. And Proxima is too faint to be seen without using a small telescope. Yeah, that's kind of a bummer, but that's how we go. The key to the discovery is, of course, the spectra. So here are some typical stellar spectra that you might take with a telescope. If you pass it through a spectrograph and take an image of it, you see that there's absorption lines in it, and there's little spectra. So the star's light gets spread out into a spectrum, and there's absorption features. And we're going to look for changes in that absorption features, specifically red shifts and blue shifts. And that's due to the Doppler effect. And the Doppler effect happens as something is approaching us or rushing away from us. If it's approaching us, we get a blue shift because the waves of light get bunched up, and so it goes to a shorter wavelength. And if it's rushing away from us, the waves of light get stretched out, or at least the interval between the successive wavelengths is longer. So the redshift occurs, and we get in the wavelengths are longer. And if there's no motion at all, we don't see any difference at all. So that's how this plot was discovered and found by watching it over the first month of over a couple, like 3 months, the beginning of January 2016. And it was found that there was a planet discovering it. And that planet makes the star wobble because the planet can't be seen, but the spectroscopy of the star evidence that there was a tiny radial velocity shift as the star moved towards us and away from us due to the reflex action of the planet orbiting the star and pulling on the star itself. So even as the Earth orbits the sun, it pulls the sun a little bit off its location because the Earth is a big thing, has a lot of mass, not enough to really swing the star around. The sun swings the Earth around more than the Earth swings the sun around, but the entire solar system, all the planets of the sun tug on the sun, and the sun kind of waggles back and forth as a result, just in the same way that Proxima Centauri gets waggled around by its little planet. And how do we know that mass of that planet? Because we're just saying that the mass is about 1.3 times that of the Earth. How do we get that? and it orbits at 7 million kilometers from Proxima Centauri. How do we get that? That's interesting. Let's see. Because this is the data that shows the discovery of a planet about the same mass as the Earth around the nearest star to the Sun. I'll let that sink in for a minute. This is the discovery data that shows it. So how do we get that? And how do we do it? Here's the end result. If we compare the Sun to Proxima Centauri, we find that the Mercury's orbit, which is incredibly hot, is very far out. It's at a third of an astronomical unit. But because Proxima Centauri is an M-type star, it is actually much cooler. So in theory, Proxima b is inside of the habitable zone, meaning if you were on Proxima b, there is the possibility that if it had some kind of atmosphere or something, that liquid water could, in theory, exist on the surface because it's not too hot, not too cold, it's just right. It's a little bit of a weird star, and it's a little bit tricky, and it goes around every 11.2 days. And the minimum mass of the planet is about 1.27 Earth masses, and the mass of the star itself is about 12% of the mass of the Sun. And its luminosity is really dim. It's 0.2% of the mass of the star, and it's a very, very, very cool star at a distance of 4.23 light years. And one of the reasons for this was the study of the stars because it might be something where people want to send a small spaceship to in Starshot. So and all of these information, all this stuff I'm showing you comes from the European Southern Observatory's public website, so you can go grab it at any time and don't get it for yourself. In fact, I'm including all the links on this thing so you can go do that. We see that if we compare the stars of sizes of relatively familiar stars, that Proxima is actually really a small star. In fact, it's only a little bit bigger than Jupiter, but it's still a star, and Jupiter's not. Why? Fusion. All right. The angular size, if you were on Proxima Centauri b, if you were on the planet, how big would the star look in the sky? And it's actually much, much, much larger. It would look really big. So if you hold your thumb out at arm's length and try to cut at arm's length during the day and try to cover up the sun, wear some sunglasses, you'll find that the sun and the moon is about half the width of your thumb held at arm's length. Well, if you were on Proxima b would be about it would be half as large as your thumb itself, and you couldn't cover Proxima b with your thumb. It would look really big in the sky. That'd be really strange to see a really big star in the sky, but that's because, well, you're a lot closer to it. So let's make an interesting thought. Imagine that there is this star. It exists. Imagine the planet is there too. And so we see in this artist's impression, because this is not a discovery image, this is an artist's impression, kind of Star Trekker or something like that. We see the yellow star Proxima b and the Proxima in the background. And we see the double star of Proxima A and B in the background to roughly their brightness. There would be incredibly bright stars in the sky because of their distance. But we see that this particular planet that does exist might orbit. It might be a rocky surface. It's only a little bit more massive than the Earth, so it would be physically larger. But what would it be like on the surface? And when we say it's in the habitable zone, we mean that the average surface temperature on this planet is conducive to allow liquid water to be on its surface. That's what we mean by habitable zone. The Earth is just on the inside of the habitable zone of the Sun, and Mars is just on the outside of such habitable zone. And we'll talk about that when we get to exoplanets later in these courses. So if you happened to be on the surface of Proxima b, the most likely place where it would be conducive for water to be on the surface is on the boundary between day and night. Because on Proxima b, it is so close to its star that it would probably be tidally locked, meaning it would only show one side to the star. Much in the same way that Io, Europa, Ganymede, and Callisto orbiting Jupiter only show one side to Jupiter, they're all tidally locked. Proxima b is highly likely to be tidally locked to the star. So the star would never change its position in the sky, just the background stars, and you would never see night on the Sun side or the Proxima b side of the star. And so the only place that might stay cool enough such that water could exist would be in cracks and valleys right at the boundary between day and night, at the twilight zone of Proxima b. And so you'd have to be right at that edge. It would be just, and if you went to the other side, it would be perpetual darkness and extraordinarily cold. And if you went to the exact equator where Proxima b would be overhead, it would probably be too hot for life. Or water, more specifically, water, if it exists in liquid form, probably exists right at the boundary zone where thermal stresses could allow some warming and some cooling. But there are other reasons probably why life cannot exist on Proxima Centauri b, because Proxima Centauri is known to be a flare star, so they can emit huge amounts of X-rays, and those X-ray flares, just like the sun has, but they're actually much more violent from Proxima Centauri. And we saw solar flares and the result on Earth, and they're extraordinarily difficult things. So we shouldn't expect that there would be a significant atmosphere on Proxima b, but it's really nice to consider that the possibility is there. And I invite you to go take a look at this from the European Southern Observatory and do follow-ups to see what people have thought in the future. But yeah, if you looked out, you would see actually the traversing of Proxima AB in the distance as you orbited Proxima Centauri. You would see Centaurus AB in the distance orbiting and changing position. So those two bright stars that you see in there would slowly change over the year. Actually, it would change every 11 days. So they would rocket across the sky as it orbits every 11 days. So this is interesting. By looking at the nature of binary stars and eclipsing binaries and spectroscopic binaries, we now not only know the masses of stars, how the masses relate to their brightnesses, how the masses relate to their spectral type, we can also discover planets around other stars. And that's a really interesting thing. And so how we know the mass, we'll talk about next time. See you soon. Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Last time we were talking about binary stars, how we get their masses, spectroscopic binaries, and eclipsing binaries, and we finished off with an amazing discovery around the closest star to the Sun, which is Proxima Centauri, and then it has a planet orbiting around it that was discovered through spectroscopic analysis of the radial velocity of Proxima Centauri. And the planet is dubbed Proxima b. What we've learned is that binary stars are incredibly important tools for the future. But we kind of left off in saying, well, exactly how? Let's make a tiny diversion this time. We're going to look at exactly how we know the mass of this planet, mass of the star. So we wanted to say that how do we know anything about this distant planet that's orbiting a star that's 4 light years away that we actually can't see, and this is simply an artist's rendition of the thing that we're looking at. Artists will make pictures and things like that, and that's the only thing I really don't like about all of these kind of things, is that the artist renditions make it look like that somebody's been there or something like that. No, we know that it's only been radial velocity data, as we saw in the previous episode. So this is a vista that's purely the imagination of an amazing artist. Okay, so how do we know the mass of the planet? How do we know the mass and distance of Proxima b from its star? So we know that this Proxima b is the official name of the planet. And why b? Why not A? Because it's the first planet discovered around that star. Well, it's because the star itself has an implied A. So the second object in the system has B, so therefore it's called Proxima b. Okay, I know, it's a little odd, but that's just the way it is. So here we go. Let's find out how we know the mass and distance of Proxima b from its star, Proxima Centauri. So we start off with the force due to gravity. Newton's law says that the force due to gravity is equal to the mass of the two stars, m1 and 2, or mass of the two objects, m1 and 2, times the Newton's gravitational constant divided by the distance between their centers of masses. And that force is always equal to some mass times some acceleration. So if we can figure out how it's moving, accelerating or decelerating, and get its distance, then we can derive a mass, and that's really what we're going to be hunting for. So remember again, Newton's version of gravity says that you have two masses attracting each other due to the force of gravity, and that force is equal to g, the Newton's gravitational constant, times the two masses, the product of the two masses, divided by the square of the distance between them. And if we then go through and look at how Newton re-derived Kepler's third law, in order not just to say p squared equals a cubed, but specifically if p is in seconds, and a is in meters, and m is in kilograms, then you can use g, Newton's gravitational constant. Now we can actually measure all of these things in terms of fundamental measurements, such as meters, seconds, and kilograms, rather than years, astronomical units, and AUs, or AUs and solar masses. But this is the equation that can be derived from Newton's laws and Newton's mechanics, and it pretty much falls right out of the equations. It's not that difficult to derive, but that's for another story, and I'll let you investigate that elsewhere. All right. First, let's assume that the planet's mass is much less than the stars, and that's a good assumption in general. So what we have is the period of the star, meaning how much time does it take for the spectroscopic variability to occur, is equal to the sum of the masses of the star and the planet. And that's, of course, Newton's gravitational constant, and for pi squared, where pi is that classic number, 3.14159, etc., times the distance between them, r cubed. So r cubed is the distance between the star and the planet. But because the star is so much more massive than the planet, in general, stars are much more massive than planets, then we can simply approximate. That's what that double twiddle means, that tilde sort of, that bent equal sign means, is that we're going to approximate the sum of the masses by the mass of the star. And that helps us get through some issues. Now, we can then say that the force due to gravity is then the g, which is Newton's gravitational constant, times the mass of the star, times the mass of the planet, times the distance r squared between them, is equal to, let's just assume, circular orbit. Now it's orbiting so closely that it's probably not a bad assumption to think that the orbit is a circle, because if it's highly eccentric, then that will eventually, that's a higher energy state than if it's purely circular. So the force to maintain something in a circle is equal to the mass of the thing at the end of the circle, or riding the circle, times the speed, v squared, of the planet going around that circle, and r between is then is the radius of the circle. That's why I used r instead of d. So again, the subscripts planet mean we're talking about the planet, and r between is the distance between the planet and the star. And we're going to assume that it's orbiting a circle, and we're not worried too much about the reflexive motion of the star due to it, so it's almost as though the star is completely fixed. And that helps us a lot. So let's combine those equations together and shorten things up and abbreviate planet with PL and abbreviate star with the asterisk. And if we just combine them together, we find that the speed or velocity around the circle that the planet takes squared is equal to Newton's gravitational constant times the mass of the star divided by the radius of the circle that the planet takes. So that's a fundamental thing. It doesn't matter. We're not approximating anything here. That's just if we're just assuming a circle. The approximation is a circle, and that the planet's going around in a perfect circle. So that's circular speed, and circular speed is pretty much what you get when you say that the mass of the object orbiting is really tiny. So we can assume that it's a circular orbit, and circular speed is pretty good. Another way to think about circular speed is take a string, put like a bolt at the end of the string or some light object that you can spin that's heavier than the string, but not by much, and spin it over your head. It'll be going in a circle because the string is as a fixed length, and it's very light. So therefore, you really don't care. It doesn't pull on your arm that much. And so you can spin something around in a circle that's really light pretty fast. And that would be v sub circle, which is the speed that it's going around in a circle. And that's equal to the square root of the Newton's gravitational constant times the mass of the big thing. In this sense, we could say that my arm is like the star pulling on it. And then r is the radius of the circle. And so all we have to do is measure the Doppler effect, or the speed with which the planet is going around. And so it's going to sometimes be going towards you, sometimes going away from you, and sometimes going across your line of sight, and it's going to vary smoothly between them. And that's how we actually get it. Remember that image that we saw from the European European Southern Observatory, which shows that the radial velocity kind of wags around like a sine curve. And so that's what we should expect. Now we can then add in yet another thing, is that when you think about a center of mass, that the planet doesn't really orbit the center of the star, it orbits the center of mass of the star and the planet's system. And so the star then orbits the center of mass system. The planet doesn't orbit the center of the star, it orbits the balance point between them. So both of them, the star and the planet, orbit that. But we can then say, well, if they have a distance between them, then the mass of the star times its speed is equal to the mass of the planet times its speed. So in this case, two people sitting on the right would represent, say, the star, because they're more massive, and on the left-hand side is the boy, and he's less massive. So if they start swinging around on the teeter-totter and remove the ground underneath them and go all the way around, then the two at the center, close to the middle, aren't going to move very fast. But the guy way out there is going to move really fast. And if they're totally in balance, then the mass times the speed at which they're going around equals the mass times the speed of the other one. So the mass and the speed of the one, such as the star, which would be close in, equals the mass of the planet times the speed of the planet, which would be the one far out. So now we have three linked equations where we have the mass of the star, the velocity of the star, the mass of the planet, the velocity of the planet, the orbital period of the star, the distance r between the star and the planet, and the speed at which the planet's going around. And all of these things, we have three linked equations, a mass planet, mass star, V planet, and we have, since they're linked, and we have a few observables, then we should be able to eliminate and get the things that we don't know. What can we do with these three equations? Well, first we measure the period of the orbit, and that's simply how long it takes for the sinusoidal orbital period to happen. And in eclipsing binaries or orbits like that we've seen, that the period is simply how long it takes to go from the radial velocity of the star going towards you or away from you, and back to the original away from you and towards you, how long it takes to vary between towards you and away from you. And then the radial speed of the star is how fast it seems to be going around in that orbit. So the radial speed of the star is what you measure, and that is the radial velocity that you get. So that was that roughly 5 or so kilometers per hour on average that it's doing at the most and the least. So that's what we see the radial speed must be. So we assume at the peak of or the trough, that's the maximum speed, and that gives you the radial speed of the star around its orbit or around its common center of mass. Somehow, you have to get the mass of the star, and if you combine that all together, you then have three equations and three unknowns. So you measure the star, the planets, the orbital period of the spectroscopy. The radial speed is how high the peaks and troughs are. And if you can figure out some way to get the mass of the star, then you can get how far the star is, how far the planet is from the star, how fast the planet's going around, and then the mass of the planet. Now, how do you get the mass of the star? Well, we did see that last time, that there's a distinct mass-luminosity relationship between the type of star, or mass spectral type relationship between the mass of the star and its spectral type, assuming their main sequence. What's a main sequence star? We haven't discussed that yet, but we will really soon, so hang on. So the mass of the star can be determined by determining its spectral type. And we'll just leave that be for a moment, and we'll just say we know the mass of the star, and there's other ways to get the mass, but more specifically, we can use such a relationship between the luminosity of the star and the spectral type, as well as extended studies of other kinds of stars and other kinds of close binaries in order to determine the mass luminosity relationship of many types of stars, and then average them together to get that. And that's what was done, and that was used by the team in order to make their measurement. So it's actually there's a lot more than just knowing or getting the mass of the star. In fact, there is no absolute mass known of the star. There's no way to actually directly measure the mass of Proxima Centauri. What you have to do is you have to measure the masses of known binary stars of exactly the same kind of stars to Proxima, such as these M dwarfs, and then know from their binaries, how massive they are from known visual binaries and eclipsing binaries, and even maybe spectroscopic binaries, that you can then determine the mass of M-type stars. And it takes a large number of them to develop the statistics in order to get it. So really the number 3 here, somehow know the mass of the star, assumes that you've measured the masses through some other way of all other M stars in the sky. Let's actually look at the first one. If you know the star's mass from the astrophysics, and we'll talk about that later, and we'll get to that, how we know that mass, and that comes from the HR diagram. Whoops, another thing that we fill out. Kepler's third law gives you the size of the planet. So we can measure the speed from the spectroscopy. We get the mass, M sub star. V sub planet is how fast it's going around, or actually mass sub V sub star is how we get it. But we'll get the planet's orbital size. So if we know the mass of the star, we know the speed of the star, we have some sort of handle on the size, we can get the planetary orbital size from these linked equations. And if you know the size of the orbit, you can get the orbital speed of the planet going around. So that's again another part of the linked equations. And plugging all this stuff in, using the knowledge of the astrophysics of lots of other observations of other binary dwarf stars, we can tell that a star like Proxima Centauri, like it, and many stars like it, are about 1.23, 0.123 times the mass of the sun, or about 1/8 of the mass of the sun. So it's pretty massive. It's still much more massive than the Earth, but still, that's what we get from such studies, and I'll post the link for that elsewhere. And then what we look at is we have the velocity of the star. It's about 5 kilometers per hour, about 1.3 meters per second, which is a very slow reflex due to the planet. The orbital period is easy because that's the easiest one to measure. It's about 11.2 days. And then Newton's gravitational constant is measured in very hook and crook ways on Earth, but that's a separate thing. That's a universal constant. Plugging those 4 numbers into the 3 equations gives us the mass of the planet being about 1.25 times the mass of the Earth. So the planet orbiting Proxima Centauri is more massive than the Earth. And the speed and its distance from it is about 5% of an astronomical unit, or about 6 times closer to its star than Mercury is. And that's really, really close. Since that's really close, we're justified in thinking that a massive star would pull that into a tidally locked orbit so that Proxima b only faces one side of the star. So that's how we do it. And then we can say, what about a physical size? So we get the mass of the planet being 1.25 times the mass of the Earth, and we assume, dun 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 dun, that the density is about the same as the Earth, or about 5,515.3 kilograms per cubic meter. And that's a really reaching assumption, but why not? Let's just start with that. That's not a terrible thing, because if it's really close to a star, you shouldn't expect an enormous amount of gas to lower the density. So maybe it's left with pretty much rocky stuff. And so let's assume it's about the same density as the Earth. And that gives us a radius of the planet about just a little bit bigger than the Earth, or about 6,900 kilometers. So it's only about 10% bigger than the Earth. And how we measure density is the mass divided by the volume. And that is the mass sub Earth, which is mass of the Earth divided by 4/3 pi r cubed, which r is the radius of the planet. And so we took the known density of the Earth, we took the planetary measurement, and it gave it the radius of the planet. So really, if we can get the mass, and we have a pretty good idea for why it might be that dense, I mean, it's that close to a star, so it's probably mostly rocky and probably not going to be as massive as Jupiter, because hey, 1.257 times the mass of the Earth, that's not going to be able to hold on to a lot of heavy gases like hydrogen or helium. So it's not going to be a gas giant, it's going to be a rocky body, and that's why we assume that the density would be about the same as the Earth. So it's a pretty good guess. So from this, we would assume that the radius of the planet is about 10 times bigger than the Earth, which is really something. That's what's really interesting about this whole thing when we talk about binary stars, and I'm just going to swing all the way back up and say, leave us with this particular thing, which is we can look at the nature of stars. And when we check out stars, we can get their masses. And when we get their masses, we learn amazing things about the nature of stars and their masses. And looking at them, we determine huge amounts of interesting data about them, not the least of which is that there's a relationship between the masses of stars and their spectral type. And remember, we talked about the nature of spectral type a little while ago, in a couple lectures ago. We have OBAF-GKM. And now we have this concept, and we see this in here about main sequence stars in binary orbits. So now we have to say, what is the relationship that we find? That this interesting relationship between the absolute luminosity, M sub V in the visual, and a star spectral type, OBAF-GKM, maybe even L. When we look at those kind of stars, we find a fascinating relationship, and that line that we see on this graph is incredibly important to all of astrophysics, and it is the basis of which we understand how the galaxy shall evolve, how we actually get stars that evolve, that where all the elements in our body and all of those things come from, basically starts from this graph, which is the relationship between the brightness of a star and its spectral type for a given kind of star, main sequence. And we'll be talking about that next time. See you soon. Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Now we've gotten to the point where we can actually put a lot of things together, from the spectral type to color diagrams, to distances, to luminosities, to temperatures, to everything, and masses, to create one of the most important tools for all of astrophysics that tells us enormous amounts of information about the types of stars, their futures, their histories, their destinies and their origins. And it's called the HR diagram, or the Hertzsprung-Russell Diagram. So let's see what that is. It's one of the most important tools of all of astronomy. Let's check it out. All right, let's go back and get our basics together. All stars are very well approximated by having their spectrum be what's called a blackbody spectrum. And a blackbody spectrum assumes that the object is hot and dense, and that the light can go inside in it and bounce around until it's completely, what we say, thermalized, so that all of the material inside of the star is roughly the same temperature. And as it emits from the surface, well, it's kind of dicey for the star, but right at the surface it becomes the same temperature. And as this light emits from the star, the surface is roughly the same temperature across the entire thing, and can be described by what's called a blackbody. And a blackbody has a particular spectral curve, as we can see here, and it's dependent upon only one thing, the temperature. And so how hot something glows and the shape of the spectrum is determined exclusively by the temperature. In fact, all these curves are exactly the same except for their temperature. They're just different scales. So if you could see them scale-free, you'd see they actually have the same exact shape, but just different curves if we zoomed in. So if we zoomed in, we see that the 3600 looks like the 7200, except that it's shorter and farther to the red. And also the curve grows exponentially as you go. All stars are approximated well by a blackbody spectrum, meaning how their light is distributed across wavelengths. Okay. Now, a key thing about blackbody spectrum is it determines a thermal radiation. So thermal radiation is blackbody radiation. And we see that we talked about this before with Wien's law for blackbodies, and the maximum the emission peak for the wavelength depends only on the temperature. So whatever the wavelength is, the hotter it is, the bluer it is, meaning the shorter the wavelength is for the wavelength of the maximum, lambda max, which is the maximum wavelength, and the cooler it is, the redder it is, so that for the peak. So therefore, Anything that's hot tends to look bluer, and anything cool tends to look redder. All right, so now if we zoom in and look out specifically at specific types of things, exactly how much energy is emitted per square unit area from a black body. And J is usually what we call the total energy radiated per unit area per second. So it's watts per unit area or watts per square meter. And that's equal to sigma, which is that little O with a hat, sigma times temperature to the fourth power. All black bodies only depend, the total energy radiated only depends on the temperature of the fourth power. So if we know that stars are roughly black bodies in their emission, then we can utilize this to help us some more. So there is a relationship between the luminosity of the star and its temperature. And what is the luminosity of the star? The luminosity of the star is the total amount of energy coming off of the entire surface area of the star. So we can use the Stefan Boltzmann law that says energy per second per unit area, and say what's the total surface area of a star, which is spherical. That's 4 pi r star squared, where r is the radius of the star, and you square it, and that little star asterisk at the bottom indicates that we're talking about a star. So subscripts always mean in equations that what you're talking about, and superscripts always mean how many of them, or an exponent. That's what we see very, very frequently throughout all of physics and all of astronomy. So when you combine it, the total luminosity, meaning the total amount of energy emitted by the entire star per second, is dependent on the radius and the temperature. Now that 4 pi comes in because it's the surface area of a sphere, and the sigma is because it's the Stefan Boltzmann law. So the luminosity of a star is proportional to the radius squared times the temperature to the fourth power. This is what's called the luminosity-temperature relation for all stars. If two stars have the same radius, then the hotter star must be more luminous. If two stars have the same temperature and one of them is larger than the other, then it's more luminous. Now, it's a really key question. Why didn't I use the word brighter? The reason I didn't use brighter is because brightness depends on distance. This is luminosity. So brightness is, well, it can be extraordinarily luminous, but if it's really far, it'll look faint, just like any star. All stars are intrinsically really luminous, but they're far, so they look dim. In fact, you can't see any of them during the day other than the sun. So this is the relationship between the total energy output of the star, its size, and its surface temperature. How can we get some of that? Because we don't measure the total energy coming off of a star. It's really difficult, and we see in the sky that we can't really easily measure the radii of stars. So how do we actually get the radius of a star? Temperature. Well, let's see what we can do. On the back of a telescope, you can put filters. And so what we see here is, again, a telescope with a filter wheel on it with a series of filters. And what we're looking at now is a standard filter set called the Johnson's-Cousins filters. And this has been around for a long time. And these are standard filters that many makers do make and create for use for astronomical purposes. And this is a Bader photometric R filter. We have these different kinds of filters. And these are commercial filters, and I just kind of nabbed it from a website. In any event, the transmission curve is what you see below. So the filters simply screw on and you send the light through that thing and into your detector like a camera or something. That's all it is. All right. So what we do is we say that color, by definition, is the difference in magnitude. Magnitude is a measure of brightness, remember? And difference in magnitudes between two filters. So with the Johnson's-Cousins filters that are in the visible wavelength region, meaning blue through red, we have three filters, the B, V, and R filter. And so all we do is we say, if something we can make 4 color measurements, and we can take the magnitude in the U and magnitude in B, minus the magnitude in V, and the magnitude in V minus the magnitude in R. We can make any two differences, but the most standard one that you'll see everywhere is the B minus the V. And that's because, well, the V is a general brightness, that R is kind of a tricky response, and B minus V tends to have the largest number of observations, and that stems from variable star observers that have been doing this for a long time. And so R tend to also not be as sensitive in photographic light, so there isn't a great historical record for it. But B and V, there is a great historical record. So there is by history and by dint of chance and by how things work that we tend to say in the standard way that one of the many colors that we can create will be the blue magnitude, the magnitude of a star when you pass its light through a blue filter or the B filter, subtracted from the magnitude of the star passed through the V filter. And that by definition is the color. So how do we get that out of there? So let's say that the difference in brightness between two colors gives us the temperature. How? Well, if we look at these spectra of stars, so we've got OB, AF, GKM type stars from blue to red on this diagram, we see an O-type star is definitively brighter in the B than the V, and an M-type star at the bottom in the red is definitively brighter in the V than the B. So remember, B magnitudes, the lower the number, the brighter. So if it's brighter in blue than in V, a very large negative number minus a small negative number will give you a large negative number. So the other way will be a small positive number minus a larger positive, a large positive number minus a small positive number will give you a large positive number, which will make a more V. That's how colors go. So the more negative the color in the definition, the bluer. So we basically take the brightness between two filters in the standard filter set, and you can see that the different kinds of stars will have different brightness, different color numbers when you subtract the V from the B in its brightness. And this is just a standard way of doing things. So that gives you the color. All right, how can we work with this? So let's start with a series of stars, and specifically what we're looking at is the center of a star cluster, and this is the center of the globular cluster Omega Centauri as taken by the Hubble Space Telescope with two filters. And one filter is an extreme red filter, and the other filter is much more blue compared to it. And it just looks like a whole slog of stars out here. But our first task is we're going to separate them out. And first, we're going to separate them out by color. And so the bluest ones we will separate out on the left, and the reddest ones we will separate out on the right. We haven't changed their location in space, but we have separated them out so we see their separation in terms of blue and red. And so these are narrowband filters that specifically isolate them. And now we're going to then say, after we sort by color, which means their temperature, means the ones on the left-hand side of the screen are hotter than on the right-hand side of the screen. And then we keep going, and we separate now by brighter. Who's the brightest? We put the brightest ones at the top and the dimmest ones at the bottom. And look at that. We've got a really interesting diagram for this cluster. We've separated them out so that the brightest are on the top, the dimmest are on the bottom, the hottest on the left, and the coolest are on the right. And we get this amazing, amazing, amazing diagram. And it is this diagram, by simply taking the brightness in two filters and comparing it to the brightness in one filter, that gives you this amazing diagram. And so we have a whole bunch of things that we can label. We've got this thing called the main sequence, and we've got what's called the subgiant branch, and the red giants, and horizontal branch, and white dwarfs, and all sorts of interesting things. So once this was discovered in 1911 by Hertzsprung and Russell, independently they discovered it, it revolutionized the nature of physics. This had to be explained. It's not random. This is an enormous discovery, and the explanation for this changed the nature of astronomy and physics. So let's go look around. We could say each group has a separate set of names. Red dwarfs are very, very, very cool and dim stars, and those are red dwarfs. And if we then look at red giants, they're also very, very cool, but they're extraordinarily bright. So we got cool stars that are both dim, and we got cool stars that are bright. And RGB stands for red giant branch. And so then we can look way over here on the very hot stars that are very dim, and those are white dwarfs, or WDs on this diagram. And white dwarfs are hot but dim. And then we have a very interesting area where this line turns away, and where one line has a knee bend in it, and that's called the MSTO, or the main sequence turn off. Remember, we're talking specifically about a cluster of stars, and that is an interesting location, and that tells us a lot about the nature of stars. And then we have a different group here called the subgiant branch, or SGB, And there's something else happening in the subgiant branch. And these are interesting stars. They're called blue stragglers, which tend to be kind of outside that. And blue stragglers have their own interesting meanings as well, and they relate to binary stars. And then finally, we have the horizontal branch, which are very bright stars and very hot stars. And so there's something going on in each of these groups, and the explanation of the physics of them leads us to the understanding of how stars evolve with time. So, in the 1990s, the European Space Agency flew a spacecraft called the Hipparcos mission, and it made a catalog of millions of stars, and here are 22,000 stars from its catalog. The previous thing we looked at was from one star cluster. Now this is from a huge number of nearby stars. So it's got a lot of stars from here and a bunch of nearby stars, and we find that there's a very, very, very great large number of stars on this group that we'll call the main sequence. So between 80 and 90% of all the stars in the sky are found on the main sequence, and that's why it's called the main sequence of stars. And so that was originally called, and the name stuck. Remember, brighter goes up, hotter goes left, not to the right, but to the left. Luminosity is small at the bottom and big at the top. And you can also see that absolute magnitude ranges from about plus 15 for the dimmest and minus 10 for the brightest. And we can see the spectral class can be put across the top as well. But most importantly, there's our color definition right there at the bottom. And color ranges from the reddest are positive colors and the bluest are more negative colors. So that's what we've learned. The more negative the number, the hotter it is, the redder it is, the more positive it is in the difference between the Johnson cousins B minus V color. So we're relating directly the color to the luminosity or magnitude. So if we can get the absolute magnitude, remember absolute magnitude on the right-hand side, is we get the magnitude plus the distance. So if we can get the distance to a star, and then we know its brightness, we can get its absolute magnitude. So if we get the distance from, say, parallax, we can get that. So this is amazing. So most importantly, we say that the luminosity can be derived from the absolute magnitude. And that's astonishing. All right, so now let's look at 85 to 90, between 80 and 90% of the stars, including the sun, lie on a diagonal band on the HR diagram called the main sequence. Now, on the main sequence, the luminosities of the stars range from about 1% that of the sun to about 1,000,000 times that of the sun. And the temperature range, though, is kind of narrow, from about 3,000 Kelvin up to about 60 or 70, 50, over 50,000 Kelvin. And the radii of stars along the main sequence ranges from about 1/10 of the size of the sun to about 10 times the radius of the sun. And basically, the small ones are at the lower left, and the big ones are at the upper right. The coolest ones are at the lower right, and the hottest ones are in the upper left. And luminosity ranges dim, not so luminous, or dim at the lower right, and very luminous at the upper left. The next group is called the giants and supergiants. There are basically two main bands of stars in the HR diagram that are brighter than main sequence. They have the same temperatures as main sequence stars, but they're brighter. So they must be larger, and that's what the luminosity temperature relation says. That if for the same temperature, if one star is more luminous than the other, it must be bigger. And so remember, luminosity is measured because of the absolute magnitude. So you can have enormous stars. The radius of these things can be 10 to 100 times the radius of the sun, and the luminosity can be up from between 1,000 and to 100,000 times the luminosity of the sun. So giants and supergiants can be incredibly bright stars. And we're looking at supergiants, which populate the most distant upper reaches of the HR diagram. Their radii can exceed 1,000 times that of the sun, and their luminosities can be up to 1,000,000 times that of the sun. And now we go down to the bottom left of the HR diagram, we find that there's white dwarfs. Now, white dwarfs are hot, but they're also physically small. And this is a really weird area because these were kind of unexpected. They were seen to be stars that, therefore, since they have the same temperature, but they have almost no luminosity, they therefore must be incredibly small. So white dwarfs are about 1% of the radius of the sun. That's about the size of the Earth. So the groups of stars that make up white dwarfs are about the size of the Earth, and we know that because we can get their luminosities from their absolute magnitudes. Their absolute magnitude comes from their distance based on parallax or something else, And parallax will get you the distance, and then you take the color of the star and the parallactic distance and the brightness that you see it to be, and you have a group of stars called the white dwarfs, which are now known to be about the size of the Earth. That's really weird. That's kind of weird. And that's what we saw with Sirius in a previous lecture. Sirius B, a white dwarf orbiting the star Sirius, and it's about the size of the Earth. So now let's take a couple looks at some of the HR diagram notables. If we then take some prominent stars, some stars that you might know if you look out in the sky, such as Antares and Betelgeuse and Rigel and Vega and Alpha Centauri and the Sun and Sirius B and all those sorts of stars. They're scattered all over the place. And if you want to look where they are in the sky, take these names down and go look them up in the program called Stellarium. But we can see that they're pretty much scattered all over the place, but the stars that you know really well tend to be at the top. You don't know Sirius B very well. Barnard's star, we only know it because of this class. And Proxima Centauri, too dim to see. So pretty much the named stars are in the upper portion of the HR diagram. Interesting. So now if we just look at specifically the 100 brightest stars in the sky, all of them have an intrinsic luminosity much greater than the sun. Many of them have a radius much larger than the sun, and many of them lie in the red giants. There's a few blue giants, and many of them are in the upper left of the HR diagram, and they tend to be B and A and F type stars. And if they're G's and K's and M's, they tend to be giants. So many of the stars that you see in the sky are most of the rare stars. They're the brightest of the stars. We don't see most of the stars. You do not see them. So they appear bright in the sky because they're really luminous stars and they're not necessarily nearby. Let's see about the close ones. What about the closest stars? If we think about the closest stars to us within, say, 10 or 15, maybe 10 or 20 light years, and you can go to atlasoftheuniverse.com in order to see more of which one stars these are. You can get a list of them. We find that all of the stars that are close to the sun are cooler than the sun and main sequence stars, and there's a few white dwarfs. There's one or two stars that are hotter, such as Procyon and Sirius and Altair, but they are within about 20, everything in here is within about 20 to 30, 25 light years, and they're really cool stars. And most of them are much cooler than the sun, and there's a significant number of red dwarf type stars, which are way down in the M's. So a number of these, Epsilon Eridani is also another interesting one that's out in the sky. Alpha Centauri is the nearest star system, and Proxima Centauri is the nearest star, which we talked about, that has a planet around it. Sirius B and Procyon B are both white dwarfs, and Procyon and Sirius, hey, they're both nearby stars, and they both have white dwarfs as companion binaries, and Procyon B is a much trickier thing to catch in a telescope. But notice that the close stars are all dim stars. Interesting. That actually, let's go back for a second. What that means is that if stars are just kind of a random sample, and we just happen to be it, it doesn't mean that only these kinds of stars live nearby us. It means that these are the most common types of stars, but they're also the least luminous kinds of stars, which means that they are the most common of all the stars. They're everywhere, these little tiny dim stars. They're all over the place. It's just the biggest, brightest ones that are the ones we pick out of the sky because they're really interesting and really cool. But the vast majority of all stars are less massive and dimmer than the sun. And that's what we learned in a previous lecture. And it's borne out because if you look at the 80 closest stars, you're taking a sample of an area of space that's kind of random around any given kind of star. And there they are, the dim stars. So we can further divide up, and let's say we can't actually get a very easy classification. Maybe it's hard to get a parallax on something, but we can always look at the spectrum. So there's a thing called luminosity classification. And if we look at the widths of the absorption lines in a star spectrum, then we can actually determine how big the star is. Okay, so if lines in a star's spectrum, those darker banded lines, become broader as the pressure increases. Why? The reason they become that the lines get broader is because under greater pressure, the atoms and molecules in the atmosphere of the star, or the atoms in the star, are moving faster. If they're under higher pressure, they're moving faster, which means if they're moving faster, there's a Doppler effect. If there's a Doppler effect, then it can absorb or emit wavelengths of light that are just off of their normal wavelengths, right? So an atom that's still, a hydrogen atom that is still, can only absorb light at 6,563 angstroms. And that also means that since it absorbs only at 6,563, that's when it's still. But if it's moving towards you, away from you, then it can Doppler shift that and absorb off of that. So the faster they're moving, the broader the lines where that happens, and that's because there's a higher pressure. Now, big stars are puffier, which means their atmosphere pressure is lower, so they're thinner lines. So therefore, large stars have narrow lines, and large stars are brighter for the same temperature. They have narrow absorption lines. And so therefore, big stars can be picked out. And so you can make a relationship, hopefully, between the narrowness of the absorption lines and their overall luminosity, and that's the goal. Well, we can have various luminosity classes, and the brightest supergiants, and this has obviously been done. And so you can look at the widths of lines, which is very subjective, but yet it seems to be easy enough to classify things into 6 different groups. And we have the bright supergiants that are the brightest of the giants, then the supergiants, bright giants, giants, subgiants, and main sequence or dwarf stars. So main sequence stars, like the sun, are called dwarfs. Everything else is a giant, unless it's a white dwarf, and white dwarfs don't have a stellar luminosity class. All right, so if we look at the various things, let's look specifically at K stars. And K stars span the range of main sequence all the way to the bright supergiants. And if we look at a supergiant bright K star, then the lines are extremely narrow. But if we then look at the main sequence version of a K1b, which would be a K star of the supergiant variety, not the bright supergiant variety, but the supergiant variety, we see that the lines are narrow because the star is puffy. Since it's puffy, the pressure is low. Since the pressure is low, there's very little movement of the atoms, so they can absorb only at their rest wavelength. However, in the main sequence star, the atoms are moving. And since they're moving, they can absorb light that's a little bit off of their normal wavelengths. And so therefore you get a broader absorption line. And if you can get the absorption features and stand them together, you find that one star compared to the other has exactly the same absorption lines, but yet one are broader than the other. If it's broader, it's main sequence, and if it's narrower, it's giant. So you can divide them up into various groups, and as you divide them up, you see that you can then relate the spectral type and the width of the lines to the luminosity, and that is distance independent, because that's just the shape of the spectrum. So that's what we do with this. This is an amazing idea because this gives you a way to assign the relative luminosity of stars based on just their spectral line properties. So you can say, well, it's this luminous, and K-type supergiant stars all have this luminosity, and so you just calibrate the whole thing, and there you have it. You can just say, I found a K-type supergiant star. I know what its total luminosity is because I know its spectral type, and I know it's a K1b type supergiant star. And therefore, you can say, well, if that's its luminosity, how bright does it look to be? And that gives you a distance, which is really cool. There's a number of giants and supergiants can be distinguished between each other, and so we look specifically at K2 type stars. Epsilon Eridani is a nearby main sequence star, and it's a little bit smaller than the sun. There's Arcturus, which is a prominent star in Bootes, the constellation Bootes in the early winter sky, and we see that going up. And Arcturus is there, and it's a red giant. But Epsilon Pegasi, which is in the constellation Pegasus, is a red supergiant. And we can see that their radii are radically different, from a little bit smaller than the sun to over 100 times the sun. And then their luminosities range from 30% of the sun to 4,000 times the sun. But their surface temperatures vary quite little, almost none at all. And so just by looking at their luminosity class, we can determine their actual luminosities, and therefore something about their radii. So the summary of all stellar properties there's a large range of stellar luminosities from 1/10,000th that of the sun in the deepest, reddest dwarf stars to 1,000,000 times the luminosity of the sun. There's a huge range of stellar radii from 1% the size of the sun, or just like the size of the Earth, like the white dwarfs, to about 1,000 times that of the sun, which are the supergiant type stars. But yet, given this huge range, there's not a huge range of temperatures between 3,000 and 50,000 Kelvin. And the mass range is also not that big. It's kind of wide, but for masses, but not as big as you might think. So it ranges from about 1/10 of a mass of the Sun to about 50 times the mass of the Sun. There are some much more massive stars, but they're exceedingly rare. And that all arises from this equation: the luminosity of a star is proportional to the radius of the star squared and the temperature of the star to the 4th power. And with this, we can plot the HR diagram, which is a plot of the luminosity and the effective temperature, find the effective temperature from spectral type or the color, make an estimate of luminosity from the apparent brightness and the distance, or even the luminosity class, and you plot that temperature from hottest to coolest and horizontal, and you get all these wonderful things. So again, the HR diagram was discovered independently, first made in 1911 by Hertzsprung, and Henry Norris Russell did a similar diagram in nearby stars in 1913. And so we use the form of Russell's as opposed to Hertzsprung. So Russell won the day in terms of the layout, but the stars don't land on just anywhere. They fall in those special regions that we've already discussed. So here's another view of the HR diagram, which is kind of a cool one. It highlights the Sun, which is a G25 type star. Betelgeuse, a winter star, is an M2 supergiant. Rigel is a B8 type bright supergiant. Sirius, one of the nearest bright stars, is an A-type main sequence star. Aldebaran, which is a K giant star in Taurus, the bull. But the most interesting thing is that why don't they have just any old luminosity or temperature? Why do they fall on this main sequence? Why are giants giants? Why are white dwarfs white dwarfs? Why are they this way? Why isn't it a scatter diagram? Why isn't it static all over the place? That's the big question. That's the central question for astrophysics. And in order to help answer that question, the Hipparcos satellite was launched in 1989, and it operated from 1989 to 93, and it made a catalog of over 1 million stars with high precision for their parallaxes to get their distances, and it took brightnesses and parallax distances, and also got parallax distances out to 2.5 million stars. And this was a major effort by the European Space Agency. And this is the HR diagram of 40,000 of the stars from the Hipparcos group. And again, they used the Johnson filter system, B minus V, and compared it to the absolute magnitude, or just the magnitude of the star, absolute magnitude of the star in its visual band. So once you have the distance from parallax, you can get the absolute magnitude. And this is the HR diagram you get, or called a color magnitude diagram. But the most important thing that happened, it was released on September of 2016, was that the Gaia mission was launched and gave its first data set on September 14th. And it recently gave out its second data set earlier this year in 2018. And yes, it will change everything. There's over 1 billion stars now with parallaxes, and has a slightly different filter system, but that filter system can be calibrated to other stars. But the 1 billion stars now give us an enormous understanding of the cosmos around us. And it was launched on 2013. It's orbiting well up past the Earth, the Lagrange 2 point in 2014, and it began in 2014 its science operations. It's going to get 1 billion stars over parallaxes for over 200 million stars, and it can get that parallax precision down to 10 micro arc seconds, which is astonishing. That means it can get distances out to 10,000 parsecs. So you really have to go take a look at this on the European Space Agency website, esa.int/Gaia, and that'll be and the first results came out in 2016. However, I just figured I'd go take a peek at their website, and we find that Gaia's HR diagram from their second data release, which they gave out earlier in 2018, was of 44 million stars within 5,000 light years of the Sun. And they're plotted on here. And this is the HR diagram from all of those stars. And now we start to see subtle changes in the HR diagram. The giant branch has kind of a hook in it. There's a lump between the HR diagram of the bright stars, and there's a dearth of extraordinarily bright stars. There's also a huge number of dim stars that are on the lower right. And the reason it kind of tapers off so quickly on the lower right is because these stars are really dim, so it's very hard to find M-type stars and L-type stars and T-type stars because they're so dim that they're almost impossible to find by Gaia. But this data set, which shows some very interesting transitions from stars descending to become white dwarfs, and as well as the giant branch with this huge number of giant stars going off to the right, is a major, major, major change. And this will change the nature of many aspects of the study of astrophysics. So just for your amusement, here's some questions about the HR diagram. And you can look at this thing and have some fun and play some games with it. And let's say, if you look at stars D and E as indicated here, which one is bigger? If you look at stars F and G, which one is bigger? Which one would be bigger, star A or star G? Which one is hotter, star E or star A? Which one is smaller, star B or star C? Which one is smaller, star D or star C? You can play all sorts of games with this thing, so enjoy. And just for the last thing, back in 2011, I was at the Hudson River Museum and got them to, and convinced them to hang a whole bunch of little things from the ceiling, little lights and balls in it. And it was a really amazing diagram of the 100 stars within the closest stars in the galactic neighborhood. So we hung them from the ceiling, and unfortunately we couldn't get totally dark and it was sunny outside. That's what that paper is in the far wall. But there's me telling things about little stars close by, and I think I'm pointing to Alpha Centauri or something like that. And all the stars in the nearby neighborhood were posted, and we had nice tours and talking about what's in the local galactic neighborhood. And here it is, another colorful image of all the stars in our galactic neighborhood as held in by the Hudson River neighborhood. And all we have to think is that these stars, most of them are dwarf-type stars, and they're very, very dim. And even this diagram, this presentation that we did at the Hudson River Museum, was something that couldn't possibly be done in like total perspective, because these stars look big, and in fact, stars are incredibly far apart compared to their sizes. So here we were walking amongst the stars and seeing their positions in the sky, but not necessarily their real positions. All right, so here's some review questions. Go over them, have a great time with those, and stop the video to see what those review questions are. And I'll leave you again with this incredibly important diagram that tells us, and that diagram and the HR main sequence, the giant branch, the white dwarfs, and all of those things are incredibly important to tell us about the future of all stars, how they evolve with time, and why they do what they do. So now we're going to be going into the evolution of stars and their birth and their death and everything in between. All right, so that's what's coming up soon, and we'll see you next time. Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're going to be talking again about the measurements of stars, and we discussed a whole bunch of different things about stars, but now we're going to actually look at something really interesting, which is the sizes of stars. As you look out into the night sky, you see these little points of light way up high in the sky, but they belie the fact that some of them are physically larger and physically smaller than each other. So how exactly big are these stars? Well, let's go back to our HR diagram that we looked at last time, and the HR diagram is a relationship between the luminosity and temperature of it. And when you relate the luminosity and temperature, you also have a definite relationship with the radius of a star. So in the upper right-hand corner are the largest of the stars, the giants and the supergiants, and the lower left are the white dwarfs. And they can range from approximately the size of the Earth all the way up to 1,000 or 10,000 times the size, 1,000 times the size of the sun. It can be really, really big. Stellar properties, as we discussed last time, depend on three things. The luminosity, radius, temperature relationship that we see here, that the luminosity, or the total energy output of the star, is equal to 4 pi r squared, r star squared, where r star is the radius of the star, and the 4 pi r squared is the surface area of a sphere. And then there's a sigma, you multiply it by sigma, which is the Stefan-Boltzmann constant, which relates the energy luminosity to the temperature to the fourth power. So the surface temperature of a star to the fourth power times its radius to the squared, times a few constants, 4 pi sigma, gets you the luminosity of the star, the total energy output of the star. And when we look at that, we find that there's a huge range of stellar luminosities from 1/100th of 1% of the sun to a million times that of the sun. And there's a huge range of stellar radii from something about a 100th the size of the sun, which is about the size of the Earth, to about 1,000 times the radius of the sun. And the range of stellar temperatures ranges from very cool, just something under 3,000 Kelvin, to about 50,000 Kelvin, which is interesting to think. It only ranges over a factor of only 20 or so. And there's a pretty big range of stellar masses between about 1/10 of the mass of the sun to about 50, or up to maybe on the extraordinarily rarest regions, 50 times the mass of the sun. But our concern this time is with R sub star, which is the radius of stars. When we actually go through and compare the different kinds of stars, we see that for main sequence stars, this is roughly how they go. And so the O-type stars are the physically largest stars, and the M-type stars are the physically smallest type. The masses are also greater for the O stars than the M stars, but really the range of mass isn't that huge, as we saw before. But the radius makes it look like there's a lot more stuff there, and frankly there is, because O stars are more massive than M stars. They can be up to 50 to 100 times the mass of the sun, where M stars can be like 7 to 8 or 10% of the mass of the sun, or even less. We see that the range of stellar sizes on the main sequence, for stars on the main sequence, can range appreciably. So this range of an M star is roughly about the size of Jupiter, and the G-type stars are the size of the sun. So an O-type main sequence star is very big compared to the sun. Let's see how we compare this. So I grabbed this off Wikipedia, which is a lot of fun, and I like this thing, so I sliced it up and had some fun with it. So we're comparing the planets, Mercury, Mars, then Venus and Earth, and we see that Venus and Earth are roughly the same size, but we're going to compare it and see, let's shrink the Earth down to that, and the Earth is smaller than Neptune, Uranus, Saturn, and Jupiter. Jupiter's the largest planet of the solar system. But how is Jupiter compared to the sun? And so let's compare Jupiter to the sun. And we see to the right of Jupiter is a brown dwarf, red dwarf type star called Wolf 359, which is an M-type dwarf in the solar neighborhood, within about 15 light years of the sun. And there's the sun right there in the middle with the orange modeling, and that comes from just some images that somebody downloaded and put together to make it look like the sun. But the Jupiter is a little bit smaller than that compared to the sun, but not by much. It's about 10 Jupiters fit across the sun. And the brightest star in the sky, Sirius, is an A-type star, and it's physically larger than the sun. And that star is about 7 light years away, and it's a big, big star. And if you go out in the winter sky, you can see Sirius in the sky. Next, if we shrink down and look at how Sirius compares to other bigger stars that we're familiar with, Pollux is and we're talking now red giant type stars. Pollux is to its right, which is one of the twins in the Gemini twins of Castor and Pollux. Then it's to Arcturus, where if you take the handle of the Big Dipper and you arc over to the bright red star, that's Arcturus. It's extremely large compared to the sun. It looks like the sun is maybe about 12 or 15 suns fit across, so that would mean about 1,000 suns would fit inside it. And if you then think of Aldebaran is a huge red giant star that's in the constellation Taurus, in the same direction as the Hyades. Aldebaran's not part of the Hyades, it's kind of an interloper, but it's an enormous red giant star. So now let's see what even larger stars are, and we go down from Aldebaran, we see, let's make that really tiny, and we have Rigel, which is one of the blue star that we see here, so that's a blue giant star, or one of the blue supergiants, and that blue supergiant is in the foot of Orion in the wintertime. And then Antares is the middle star here, and that is the heart of the Scorpion and Scorpius. And Betelgeuse is the farthest right one, and Betelgeuse is the bright red star in the shoulder of Orion in the wintertime. So if we keep scooting down and say even larger stars, some of the largest stars known are Mu Cephei, VV Cephei, and VY Canis Majoris. And the reason they have that strange designation is because these are variable stars. All 4 of these are variable, and they're enormous. In fact, VY Canis Majoris is one of the largest stars known. And if we take a peek at how big it is, we see that VY Canis Majoris is so large that it would insanely dwarf the sun. The sun looks like a tiny, tiny, tiny speck, or roughly the size of a small one of Saturn's larger moons, not Titan per se, because that's pretty big, but one of Saturn's maybe smaller moons compared to the sun. The VY Canis Majoris is so insanely large. It would be much larger than Jupiter's orbit, much larger than Saturn's orbit. It's one of the largest stars known. So this is another red supergiant star. And clearly VY Canis Majoris at some point will stop doing what it's doing and do something else called supernova. We'll talk about that later though. So now if we move along, and then we see on the other side of the spectrum, the white dwarfs, which we said, oh, they're always down there and that. This is the typical size of a white dwarf. So white dwarfs are about the same size as the Earth. They have roughly the same mass as the Sun. So they're much, much, much more dense than the Earth. We demonstrate here that the escape velocity is about 2% the speed of light, which really is much, much, much faster than escaping from the surface of the Earth. And if we then compare it to someplace in the sky, that one of that we know that in the sky is Sirius B, which is the white dwarf orbit in a co-orbit with Sirius A, the brightest star in the sky. So not only is Sirius the brightest star in the sky and one of the closest stars and an important A-type star, it's also a binary star as we saw before, and its companion is a white dwarf. And the white dwarf can actually be seen in a small telescope, and this comes from the Hubble Space Telescope when they're trying to determine the mass of Sirius B, utilizing the fact that if it's got 2% the speed of light for an escape velocity, then it should have a significant gravitational redshift to the spectral lines coming off it. And so this is part of that study. So stellar radii in general are extremely difficult to measure directly because they're really far away. So if you're about a parsec away, the sun will be less than 1% of an arc second. That's really small. And remember, an arc second is the same as a football edge on 37 miles away. So then you'd have to take it even farther, 1,000 times further away in order to get, or 100 times in this case. So that's a really, really, really small thing to see. And you probably couldn't see it. So stars are apparently small because they're so far away, but they're not actually small. They're not physically small. They just appear small because of the angular size, because they're so far away. And so in order to see them, you can use interferometry, which says that you can say on single stars, you have some sort of large baseline and you try to measure the size with respect to background stars. Then you can have lunar occultation. So if the moon passes in front of the star, then the star will dim. And as it dims, that belies its size. So if it dims rapidly, it's small. If it dims slowly, it's big. And then if you have an eclipsing binary, you still need the distance to the star, but the eclipsing binary definitively shows the size. And occasionally, the stars are big enough and close enough that you can actually directly image them, such as Betelgeuse. And so not very many stars have had their sizes, their direct sizes, their radii measured. But let's take a look, for example, at Betelgeuse, an example, and this is from Babak Tafrishi from theworldatnight.org, and it's also when he likes going to European Southern Observatory and taking some amazing photographs of the southern sky. And we see right off on the right-hand telescope there, just above that, above it and to the left is a reddish star, and that reddish star, I'll mark it with my mouse. And the reddish star is Betelgeuse. And if it looks kind of weird to you, it's because it's in the southern hemisphere. So Orion's upside down when seen from Chile. So that's kind of interesting. So this is from the European Southern Observatory, taken by Babak Tafrishi. Anyway, Betelgeuse is a great example of what we're going to be talking about. Betelgeuse is a red supergiant star in the upper right-hand corner of the HR diagram. And it is a bright red star, and it is a star that's bright at red. It's red because it's bright at red wavelengths, and this is a typical spectrum for an M-type star. And let's see, because therefore it's brighter in the red, so they'll appear red in the sky. So it's an M-type star, and we then see because we know it's a supergiant, because remember that the difference when we looked at luminosity classes, that a main sequence M dwarf type star will be compact. And since it's compact, the atoms and molecules hit each other and are moving quicker and they're under greater pressure. If they're under greater pressure, they can absorb and emit light at slightly different frequencies than the atomic frequency that would normally be emitted or absorbed at that wavelength. Say hydrogen could absorb not just at 6563 angstroms, but maybe 6566 and down to 6550 angstroms. So that would be something where you'd see for a dwarf star. But in a supergiant star, there's almost no pressure because it's all very feathery and gossamer in the outer regions. So there's almost no pressure. So there's no pressure broadening because the atoms and molecules aren't moving as fast. So you don't get as much broadening. They get Doppler broadening, but that's a different thing. All right, so Betelgeuse is really big. And that's how we know it's really big, is because of the luminosity class inside of its spectra. But its size can actually be measured. And Dr. Dupre at Center for Astrophysics back in '95 actually measured the size of the star. And we see that it's much bigger than Earth's orbit. And you can see that it actually doesn't have a spherical appearance. So it's kind of a weird looking star. And in fact, a group of people at the European Southern Observatory took a long image of it. And this was from the VLT, or Very Large Telescope in Chile. And they used some adaptive optics and found that they were able to get resolution using this adaptive optics down to milliarcseconds. And so it's a really tricky thing to see, but they were able to do so in the near infrared so that they can actually have higher resolution. So then they took that, we can take the image that we saw previously and we see how it compares to the image that was taken with the Very Large Telescope by this group. And then, if we then pull out even further, we see that actually even larger than that, and this is by Curvella and group using the VLT, we see that the previous image is actually compacted inside of a much larger image. That is a huge, huge, huge area of extended glow and emission around the star. And this star is actually much less of a spherical distribution than waves of stuff coming out. We're going to see that this contributes to the star being highly variable, and because it's a variable star, it's an interesting thing to watch. And one day this star may explode as a supernova, and those clouds around it that are coming off of Betelgeuse. And each red ring that I've shown you previously is the previous image inside of the other one. And all of this stuff comes from Curvella's group at European Southern Observatory, taken by the Very Large Telescope. This is an artist impression of what it might look like, and so you can pretty much think that this is an enormous, catastrophic lava lamp in the sky. And when we look at huge, huge, huge stars like this, they tend not to be spherical in their distribution, but that's exactly what they do look like. They're enormous, enormous objects in the sky. And what's interesting is Betelgeuse is a good star to learn variable star, naked eye, or telescope, or small telescope, or even photographic observations with, because it varies randomly because of its puffy outer shape. So one day it might go supernova, and we'll talk about that pretty soon. So see you next time. Hello everyone, this is Jason Kendall and welcome to the next of my introductory astronomy lectures. This time we're going to be talking about masses, luminosities, and ages. So we're really getting to the important stuff in the HR diagram here, which is what we really can learn by looking at the HR diagram in great extent. Once again, the HR diagram is a plot of the luminosity up and down versus temperature left and right, with increasing temperature going to the left. And cooler stars on the right, hotter stars on the left, dimmer stars at the bottom, and brighter stars at the top. And by brighter, we mean more luminous, not brighter in the sky. And that's a difference that is important to note. But there's an incredibly important element to the HR diagram, and that's the main sequence. And the main sequence is where up to 80% of all the stars in the sky live. So if you make this plot, The giants and supergiants and white dwarfs are the minority of all the stars. Everything pretty much is on the main sequence. So let's see what the consequences of this observation are. So the first thing we looked at was last time we talked about the radius of stars, and we demonstrated all of the various radii that stars can be, from white dwarfs all the way up to supergiant stars. But we find that if we take for specifically main sequence stars, the radius of the star doesn't vary a huge amount. It varies from about 10% the radius of the sun for stars that are about 10% the radius of the sun for stars about half the mass of the sun, all the way up to only about 20 times, 10 times or so the radius of the sun for very massive stars. So the radius of a star for main sequence isn't really that big. And the sun is only about 10 or so times smaller in diameter or radius than the largest, most massive stars. That's interesting. So the radius of that doesn't vary, varies only small with respect to the mass. However, even though the radius and mass vary roughly about the same, the luminosity and mass do not. So really, really massive stars are extraordinarily luminous compared to the sun, and really dim, small mass stars are extraordinarily underluminous compared to the sun. So while the radius, let's go back and look, the radius of a star for main sequence varies almost the same as the mass. As you can see, the radius ranges from about 1 to 10 solar masses, but the 1 to 10 solar radii, meaning compare it to the radius of the sun, and the mass varies about that too, roughly between about a tenth or so, or 10% the mass of the sun, only up to about 20 times. So these are roughly in the same bucket. But if we look specifically at luminosity, it's really not the same. So we have to then ask the question, wow, this is really interesting. If the radius doesn't vary very much across this, but the luminosity does, then there must be some sort of relationship between the mass and the temperature of a star. And there is. And in fact, there must be an incredibly important relationship between the mass of the star and its luminosity, as we can see here. So for main sequence stars, the stellar luminosity is a definitive function of mass. And let's see what we really mean by that. We can kind of get into some details, but let's bring it back to an HR diagram sort of look. Because if the star's mass is a function of its luminosity, as we saw previously, then, and therefore if the main sequence is where most stars live on the HR diagram, then mass is the sole determinant of where a star is on the main sequence. And therefore we can also then relate the surface temperature to the mass. And we can do that pretty well because there's the luminosity radius temperature relation that we looked at before. So now we can actually try to link the mass of the star to its surface temperature, and therefore the surface temperature, as we looked at previously, is the only thing that determines the spectra. So really, if we can figure out a very good relationship between the mass of a star and its temperature, and the temperature for main sequence stars is deeply linked to the spectral classification, then if you know the spectral classification of a star, you know its mass. And all you have to do to determine the mass of a star is look at its spectrum, as long as it's a main sequence star. All right, that's really interesting. And let's see how well we can know that. This is, again, the mass-luminosity relationship that we looked at before in the binary star lecture by T.J. Henry, that shows definitively that there is, in close binary stars in the solar neighborhood where we can get decent binary star masses, that there is a very good empirical relationship between main sequence stars masses and their luminosity, and therefore their spectral type. So you can see on this graph we have the mass at the bottom going big to the left and small to the right, and then we actually mirror that with the spectral type OB/AF/GKM on the top of the graph, meaning hottest is to the left and coolest is to the right. And then we can put the absolute visual magnitude, and we can see that there is an enormous variation between, say, 1,000th of the, just a little less than 1,000th, more than a little thousand, like about 1% of the luminosity of the sun, all the way up to millions of times the luminosity of the sun. And that's up in the O's. All right, so here's some familiar stars just to get some of that stuff and see how their masses and their central temperatures and their surface temperatures. Actually, we're deviating away from the surface temperature and looking at the central temperature and their luminosities, which are related to the surface temperature, and how long they're expected to live. So if we look at a B-type star, which is Spica B, and Spica B is a B2V, and that V in their luminosity class indicates that it is main sequence. So an A-type star, a B-type star, a G-type, an M, and then the subclassification 2, 0, 1, 2, 2, and 5, and then the V indicates it's a spectral luminosity, that's luminosity class is main sequence. So those luminosity class and spectral type are easily seen by simply doing an observation of the spectrum, and that's what you can get. And all the rest of the things that we see on this graph are derived. Now, presumably, maybe we can get the mass from some other thing, such as an orbiting companion or something like that. And that's the only way to get masses directly, is from some sort of dynamic thing that shows movement. And that's why binary stars and close binary stars are so incredibly important, because it calibrates the second column. The central temperature strictly comes about as a result of the physics of fusion, and then the luminosity can be derived from observations taken at absolute magnitudes in the visual range and extrapolating, assuming a black body, and then we can make an estimation of how long the star will live in millions of years. So we see that Spica B might only live to about 90 million years at about 800 times the luminosity of the sun. Vega, one of the brightest stars in the summer sky, is about 50 times the luminosity of the sun, and it's only about 3 times the mass of the sun, or 2.5 times the mass of the sun. So really there's not much difference between the masses. I mean, there's 2 times, roughly a little bit more than 2 times the mass difference between Spica B and Vega, but yet the lifespan is about 6 times longer, and the luminosity 10 times less luminous. So you can see that a small change in mass leads to a large change in luminosity and a huge change in lifespan. And if we decrease the mass just even a little bit from Vega to Sirius, the mass drops by only about half of a solar mass. The central temperature doesn't drop too much, but the luminosity drops by a factor of 2, and the estimated lifespan jumps by a factor of 2. And then we look at a star just like the sun, Alpha Centauri, and Alpha Centauri is a little bit more luminous than the sun, about 1.5, 1.6 to the luminosity of the sun. And so its lifespan will be shorter than the sun. And the sun's lifespan is going to be total about 10 billion years. That's what 10,000 million means there. And Proxima Centauri, the nearest star that we saw that has a planet orbiting it, is an M-type dwarf star with about 1/10 of the mass of the sun. And its luminosity is incredibly small, 6,000ths of 1% of the luminosity of the sun. That's a really dim star. And therefore, it'll live to be about 16 trillion years. So there's something interesting. Let's see how we derive this table. But first, let's note that because of that, we went through and showed how many stars exist in the sky of various types. And massive stars are incredibly rare. Most of the stars are red dwarfs, or solar-type mass stars. In fact, the brightest stars you see in the sky are incredibly rare stars. And stars like Proxima Centauri fall deep in that orange-brown zone of the red dwarfs, which are much less massive than the sun. So about 70% of all the stars in the sky are half the mass of the sun or less. So what do we mean by main sequence? All right, so now we're going to go into what makes up a main sequence star. We're going to utilize what we learned about the sun to do that, because the sun's on the main sequence, and all these stars are on the main sequence. So what makes up a main sequence star? We can say that the following 2 things must exist. The star has to be in hydrostatic equilibrium, meaning pressure is balancing gravity. And that's what the diagram on the lower left is all about. There's a pressure coming in from all the weight of the material that indicates the blue arrows that are pushing in on the core. And then that's the gravitational push, which is the blue. And then the red arrows demonstrate the outward pressure because it's hotter. So hot pressure gas will exert a pressure against gravity above it. So gravity's pulling in, the pressure is pushing out. And it also has to be in thermal equilibrium. And thermal equilibrium means that of the two arrows on the right-hand side means whatever is produced in the core gets emitted at the surface. And for the surface to stay the same luminosity, the core must stay roughly the same luminosity. So all of the energy that's generated and seen that comes off the surface of the star had to have been generated deep inside the star in the core. So that's what the two red arrows mean on the right-hand side. However, if you change any of this stuff, then the star will evolve away from the main sequence and over time change its position on the HR diagram. If we plot the luminosity as a function of mass, and we applied this because we learned that there is a mass-luminosity relationship. In fact, that's what we saw before, is that if we look at the nature of the luminosity as a function of mass, we get that main sequence stars' luminosities are strongly correlated with the mass. That was shown in the previous studies. But roughly it goes like if you compare a star's luminosity to the sun, it's equal to the star's mass compared to the sun to the fourth power. Now this relationship does not apply to giants, supergiants, white dwarfs. They are not main sequence stars. And you'll notice there's kind of a knee at the bottom end there, which doesn't quite follow this relationship. So it's not strict, as we've seen in the previous thing, that it's not strictly this relationship, but it's a good place to start. That's why we have that little fishy symbol, which means proportional. All right, if the main sequence is a mass sequence, the location is completely determined by its mass. Why is that? Because the luminosity is the energy production rate, how much energy it must produce. So if it's more luminous, it must be burning up its fuel faster. And if it's burning up its fuel faster, it must have a shorter life. So there's not a huge range of masses from, say, 1% the mass of the sun to, say, 100 times the mass of the sun. But yet the luminosity is incredibly different from low mass stars to high mass stars. So therefore, high mass stars must live shorter and low mass stars must live longer. And let's see why that is. In the upper main sequence, where stars specifically have masses just more massive than the sun, about 10% or 1.1 times the mass of the sun, 10% more massive than the sun, the core temperature rises to above 18 million Kelvin. And when that happens, hydrogen fusion doesn't pass through the proton-proton chain. It uses the CNO cycle, or carbon, nitrogen, oxygen cycle, where carbon, nitrogen, and oxygen nuclei act as catalysts in order for the fusion of hydrogen to helium to occur. And interestingly enough, this means that there's a huge amount of temperature differences, or the temperature gradient inside the core is huge, and the density is high. So therefore, the core is convective. And that means the center of the star really churns hard, meaning there's an enormous burbling churning. However, if you look at the surface of the star, it would be radiative. So it'd be a very different appearance. So to look at hot stars up close, if you could see them, would be kind of smooth. They wouldn't have the convective cells that we see on our sun. That kind of the granulation and supergranulation would not be present in a radiative envelope star. So an OB type star or an A type star would have a very smooth appearance at its photosphere, which is really fascinating. All right, so then we do look solar type mass stars, less than 1.1 times the mass of the sun, which includes the sun. The core temperatures are less than 18 million Kelvin. That means the proton-proton chain is the dominant way that energy is produced in the core, and they'll be roughly like the sun, where the core is radiative transfer, meaning there's not such a huge temperature gradient in the core. And since that gradient is not so big, you get a radiative transfer of energy. But that means the outside is cooler, and therefore you get convective flow. And so stars like the sun and a little bit less massive than the sun are convective at the surface. But if we go deep, deep, deep into the lowest mass stars, between about a quarter of the mass of the sun and about 8% the mass of the sun, and yes, there is actually a minimum mass, and they only do the proton-proton chain, but they're fully convective from core to surface. That means a nucleus of a hydrogen atom will appear will get to the surface, and then the convection will bring it all the way to the core. So the entire star gets churned, where the other two types of stars have convective regions. The sun's convective region does not reach to the core, and the convective region of massive stars does not reach to the envelope. Therefore, these red dwarfs, which are the most populous stars in the cosmos, which make up almost half the stars in the universe, are these little tiny crockpots that just cook everything low and slow. And they make these wonderful stews over the course of time. But then they don't do too much other than that. They live a huge, huge, huge lifetime. So what happens as a star gets older? And this is kind of an interesting question. Actually, stars get brighter with age. Again, main sequence stars are in hydrostatic equilibrium and thermal equilibrium, which is hydrostatic on the left, where pressure and outward pressure due to the heat is balanced by the gravitational pressure pulling in. And then thermal equilibrium means that whatever is produced in the core must get to the surface. That means that the central temperature is highest in the core of the star. And therefore, if you have an ideal gas, pressure equals density times the temperature. So the temperature says the average speed of the nuclei as they zip around. All right, so the pressure means the density times the temperature. Temperature indicates that the average speed is higher, so higher temperature means higher pressure, which means they're moving faster. If they're moving faster, the density therefore is defined as the nucleus per cubic centimeter, how many nuclei are in there. And the number of hydrogen nuclei gets reduced with time. And you have to have a high temperature in order to do fusion. So as fusion occurs, there are fewer hydrogen nuclei around as the hydrogen nuclei become helium nuclei. And here the P indicates protons, which are hydrogen nuclei. H over the 2 is deuterium. And He is a helium nucleus with two protons and one neutron. And then when they collide, they form a normal helium nucleus. So the top two equations happen twice. And that means that four objects, protons, become one helium nucleus. So the total number of protons decreases with time. As a consequence of that, the remaining nuclei have to move faster. So as the hydrogen nuclei, which are the fuel, they've got to move faster in order to maintain the pressure. So in order to resist it, the gas has to get hotter. If it's moving faster, it has to get hotter. So therefore, as time goes on, the center of a star, such as the sun, gets hotter over time as the hydrogen gets converted into helium and the density grows higher because the pressure is getting higher, because the temperature is getting higher. The higher core temperature causes fusion, therefore, to run at a faster rate. The star gets brighter with age because the core temperature gets higher, so therefore the luminosity in there, if the fusion gets higher because the temperature is rising, and the temperature is rising, that means the luminosity is rising. Therefore, there's greater luminosity in the core, and that luminosity must make it to the surface. And so therefore, stars get brighter as they age. The sun is no different. The sun in its youth was cooler, and there's evidence for that geologically, which is really fascinating. Now, the sun's radius won't change too much on the surface. Well, actually, the sun's surface temperature and its radius kind of balance out that extra luminosity. So very slowly, the sun's radius is growing, and very slowly, the sun's surface temperature is cooling. So the temperature is getting a little less over time, but the radius is getting a lot larger. So when we see these T sub star, that's the temperature at the surface, not at the core. It's a tiny effect. So every 100 million years, the sun gets a little bit brighter, meaning just under 1%. So you're never going to see it on the human timescale. And it's not going to be a global warming thing. Sorry, this does not drive climate change. Although it does over 100 million or billion year timescales. That is true. It just does not do it over the last, say, 1,000 years, which is the dominant change for climatic change. So no, this is not a climate change driver. However, there is evidence from geologic time, and we know that in the last 4.5 billion years, the sun has gotten about 30% brighter over its lifespan. That's interesting. So the sun's gotten brighter over the last 4.5 billion years, but it hasn't jumped in brightness in the last 1,000. So all the heat and the temperature rising on Earth is due to us, not the sun. Now, how long can the sun do this? Or any star can do this process? Because as we saw, hydrogen is being converted into helium. And so therefore, the total amount of fuel it has is the mass of the star, and how fast it's burning is the luminosity. And therefore, we should be able to get a time that it can live. And that's what this little equation says, the tau sub nuc, which is the time that it can do nuclear fusion. And it's dependent on a number of things. The fraction of matter, F, that is involved in nuclear fusion, the efficiency of that matter energy conversion, which is the little e for epsilon. Mass is the total mass of the star. So really, it's the efficiency times the total fraction of F times m. It should be, really, because that's the fraction of the mass that actually goes into it. And then the speed of light squared, which is that E equals mc squared thing. So it's really E equals mc squared times the fraction that's participating in E equals mc squared times how well it does that. And then you divide that product by the luminosity, which is the energy that's emitted per second. So really, the top of the equation is energy. How much energy is produced by the mass of the sun every second, and how efficient is it, and how much will it do? And therefore, you can say over the total lifespan of the sun, the total amount of mass, assuming the same luminosity, and we get the nuclear timescale. The nuclear timescale, in turn, depends on just the mass and the luminosity. But we know that there is a definitive mass-luminosity relationship for main sequence stars. And if we combine them together, we find that for main sequence stars, that there is a definitive main sequence lifetime. And that tau sub main sequence is proportional to the inverse mass cubed. I'll let you look back and see why that is. The bigger they are, the shorter they live. And therefore, so a massive star that's 10 times the mass of the sun has only a 10 million year lifespan. The sun will live about 10 billion years total in its lifespan, and something 10% the mass of the sun will live 10 trillion years. And it's interesting to think, okay, when looking at the numbers like this, side note, is that if you were to go to London and say, what's a billion? They'd reverse billion and trillion. And why do they do that? Because a billion to a Brit is by million. And so if you look at million, by million, what's by million? A million is 6 zeros. Oh, a trillion has 2 sets of 6 zeros. So it's a by million or a billion according to a Brit. But in the US, we call it a trillion because it has, well, I don't know, 3 groups of 4, I guess. So that's kind of weird. But, there's billion, million, trillion. I guess we say billion for 10 to the 9th and trillion for 10 to the 10th because by, then try, I guess, whatever. I like the Brit way. But just to keep things straight, the massive stars live about 10 million years, the sun lives about 10 billion years, and a low mass star lives about 10 trillion years. And that's all because of how fast it cooks the hydrogen in the core. So there's some consequences to the observation. And so we go back to this main sequence luminosity, this luminosity mass spectral type relationship. So if you see an O and B type star and its main sequence, it has a very short lifespan. It will not live very long. It'll live on the order of a few tens of millions of years. So therefore, some of the stars in the sky, the O and B type stars that you see in the night sky, were not there 10 million years ago. In fact, every O and B and A type star you see in the sky did not exist when the dinosaurs roamed the Earth 65 million years ago. Wow. There were different OB type stars in the sky then for them to see, but not the ones that we see. Therefore, Orion's belt was not in the sky for the dinosaurs. It also means that we know that the sun is about 4.5 billion years due to the age of meteorites on the Earth. Therefore, the sun is halfway through its main sequence lifespan. It's about 4.5 billion years along. It'll go for another 4.5 or 5.5 billion years before it starts to change its position on the HR diagram. And this isn't an HR diagram, this is a mass luminosity diagram. And for the M-type dwarfs, it's really not possible to know their age because they don't evolve very much as they age. So we can't tell if an M-type star is a young M-type star or a truly ancient M-type star because they just cook low and slow, so we have no idea. So therefore, O and B-type stars, they're young. And we know that there are some observational characteristics that allow us to determine the ages of F and G type stars and some K type stars. but there's almost no way to determine an isolated M-type star's age, which is really fascinating. So there's some observational characteristics of it. But the really important thing that we see here is that the mass is related to the spectral type. The spectral type is related to the age for main sequence stars. Don't be fooled by this, because if I show you a giant type M star, it could have been any of things. It could have been an OBAFGK type star some time ago. But this relationship and how old it is only applicable to main sequence stars. So how long they live on the main sequence is all we've been talking about. Not what happens after they're done being on the main sequence. We'll get to that really soon. Very soon we're going to be going into how stars evolve, but first I want to show you, before we look at stellar evolution, we're next going to be looking at how stars are grouped and how they're formed, and how we know the ages of stars to begin with, and how we got this idea that we just talked about. Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We're rounding out the nature of measurement of the stars and stellar measurements in general, and we're going to link a whole bunch of things together in order to get distances. So distances were first introduced to us with parallax, and the Hipparchus mission, which ran in the early 1990s, generated an enormous list of parallaxes to nearby stars. Roughly about 1 million with really good precision, and about 2.5 million with poor precision. In any event, the highest precision measurements are approximately 100,000 or so stars from this particular mission, and parallax was incredibly important just to do this measurement. So the Hipparchus satellite changed astrophysics when it did it. However, the Gaia mission, which was launched in 2014 and then did its first data release in September 2016, changed even more things. And its data, will actually get parallaxes for over 200 million stars and get proper motions and positions for 1 billion stars. So its maximum precision was about 10 micro arc seconds, or about 1% of a milli arc second. And so that means it can get distances out to 10,000 parsecs, or approximately a quarter of the way around the galaxy, which is really amazing. And definitely almost to the center of the galaxy, if you could see through things. So I put the website link for the Gaia mission there, because it's one of the most important missions. And it doesn't make pictures. It doesn't make pretty pictures like the Hubble Space Telescope, but yet its impact will be greater. The trick is that we're actually going to find that we can use the distances to stars, or actually derive the distances to stars, by simply looking at the brightness of two stars in two different standardized filters. And we'll call those filters the Johnson B and Johnson V, because they tend to be the most widely used. But of course, things are used in different filter techniques. You could do that too. Notice we have, from the Hipparchus satellite, we have an HR diagram, about 22,000 stars. And there is a link between the color of a star for a main sequence type star and luminosity. And you can see that the trick is that, well, what about those giants and the white dwarfs? They kind of mess things up. But if you can somehow assure that you've got a main sequence, then you can actually determine the distance of things, because you can calibrate, because all stars fall on this main sequence. Doesn't matter where they are. If they're a main sequence star, they fall on the main sequence. So if you can get a group of stars that happen to be at the same distance, then they may have a distinct main sequence. And if you can use that, then you can get to find this group of stars. And that is called spectroscopic parallax. Spectroscopic parallax doesn't really have a lot to do with geometric parallax, but it does actually. It actually uses spectroscopy to find the distance. So what we're going to do is we're going to measure the apparent magnitude or apparent brightness of a star and its spectral class, or its color. Spectral class is much more important, actually, but that involves a good spectrum. But color, with just a difference in brightness of two filters, which is much easier and more common. And you can find the luminosity class if you can, but then to get the luminosity class, you definitely do need the spectrum, unless it's in a cluster. And then you can apply the inverse square law to find the exact distance. Or you can use the distance modulus equation, which we'll look at later. Spectroscopic parallax in greater detail is a distance-independent property. So that's the parallax itself, but the observed spectrum. So if you can get a high-resolution spectrum, that tells you the star's temperature. The star's temperature gives you the luminosity, as we've seen from the luminosity radius temperature diagram. So if you have a good knowledge about the nature of the luminosity class, which means that it'll tell you where it is on the HR diagram, and that unique location on a calibrated HR diagram gives you the distance. How do you do that? Well, first you make an enormous HR diagram of as many nearby stars as you can, and you make sure you get a good parallax for all those stars. And the most important group of stars in the sky is the Hyades star cluster. That is the most important one. And because it's the closest star cluster, and it's a relatively young star cluster. So it's the most important thing, and we'll see why shortly. And then what you do is you get the spectral type and luminosity class of some star from its spectrum. Remember, though, that the widths of lines depend on the luminosity class. And then you locate the star in the calibrated HR diagram and just simply read off the luminosity, and you compute the distance from the measured brightness of the star. So you know what the luminosity is because of the calibrated HR diagram. And then from that, you can get the distance, given that you can measure its apparent brightness. So how does this look? Here we have kind of a sketch of an HR diagram, and we see a bunch of stars on a main sequence, and there's a first one that says, well, what type of star it is. It is an A8V, which means it's type A, spectral type A, subclass 8, and luminosity class V, or dwarf. And if we have a calibrated HR diagram, meaning we know exactly what the luminosity of all A8V type stars are, then all we have to do is make sure that we have one of that, and that gives us the luminosity of it. It may be 10 times the luminosity of the sun. Maybe it's that. And then if you find that it's very, very dim, then it must be very, very far. And so you calculate exactly how bright it would be compared to the sun at such and such distance, given that it is 10 solar luminosities, or 10 times the luminosity of the sun. How far away would something have to be in order for something 10 times the luminosity of the sun in order to have the brightness that you observe it to be? Also, the same thing is that you might get distracted and say, oh, it's also it's a spectral class A, subclass 8, but it is a bright giant, which would mean a luminosity class 1. And so that would be, as a bright giant, 22,000 times the luminosity of the sun. So now we have two stars with the same spectral class, but different luminosity classes, which lead to incredibly different luminosities, and therefore different distances, if you measure them to be the same brightness. An A8V star with the same brightness in the sky as an A81 star, then the A8V star must be much closer than the A81. So if they were at the same distance, then the main sequence type star, the V luminosity class, would be very faint compared to the other. So our best thing, though, is we need to calibrate the HR diagram. So let's see what we can do. And again, let's just look at the various luminosity classes, as I jump the gun there a little bit, because I always forget what the order of my slides are, and it's just how that goes. Luminosity classes, there's roughly about 1, 2, 3, 4, 5, 6 sort of luminosity classes. There's two different groups of supergiants. One group of bright giants, then there's subgiants, and dwarfs. Everybody's a dwarf that goes on the main sequence, even though that some of them are pretty large. It's just how they're classified. White dwarfs are not given in this diagram. But again, remember that the larger the star, or more specifically, the closer to luminosity class 1 they are, the narrower the lines. And the absorption lines for main sequence stars are the broadest because they're the densest stars. And density means higher pressure. Higher pressure means the atoms are moving faster in the atmosphere of the star. And if they're moving faster, then they can absorb and emit wavelengths of light that are off of the normal wavelengths of the atomic transition of that particular atom. But when they're giant stars, the atoms and molecules are under low pressure, which means their relative speeds are lower, with respect to each other, so you get less and less Doppler broadening of the lines because the atoms and molecules are moving slower, so they can really only absorb at the wavelengths that are corresponding to the atomic transitions. So that's why the luminosity classes are different. Here's some difficulties with doing this thing, and it's really hard to use it for individual stars, and it works best for star clusters. We're going to talk about that in just a little bit. And despite the name, it only uses geometric parallaxes to initially calibrate the HR diagram, make a massive calibration. So global studies such as Hipparchus and Gaia are critical because that helps you to calibrate the distance. So you use massive numbers of geometric parallaxes to calibrate the HR diagram. And once you've done that calibration in the geometric parallaxes, you don't no longer use geometric parallax because the goal is use the spectrum, not the parallax. Maybe you can't get the parallax for this particular star, but you can get its spectrum because the spectrum is in the light, and that's what you're observing. You don't directly observe parallax unless you wait for the Earth to move around the sun. And so that typically is not how long it takes to do a spectrum. In any event, the practical distance is about to 100,000 parsecs, but really that's best for star clusters. And this is now well extended due to the Gaia mission. The luminosity classes are really roughly defined, so that makes it trickier because, yeah, you're talking about widths of lines. So as you can see from the HR diagrams that we've shown, that once you put a huge number of stars out there, the luminosity classes start to blend together. So you really do have to, it's a bit of a trick. So there's a bit of hand-wavy magic with number 4 there. And if you have faint spectra, well, it's really hard to tell the main sequence star from a giant. It actually gets very difficult if the spectra are very, very faint. And we haven't really talked about this too much, but the HR diagram location also depends gently on the composition of the stars. So that will come into much later when we think about the nature of how much hydrogen and helium and other elements are in the atmospheres of the stars. And so if there's slightly different composition to the stars, meaning or significantly different, it's always hydrogen and helium are the dominant things, but what the other stuff is, what the proportion of the rest of things like carbon, nitrogen, and oxygen, iron are in the atmospheres, that will affect the location of the star in the HR diagram. But for an introductory purpose, like an intro astronomy thing, number 6 is not really our main thing. The main thing for the difficulties with spectroscopic parallax and introductory level, because it's, spectroscopic parallax is not parallax. And luminosity classes are hard to do, and faint spectra are really tough to use. So getting good spectra is critical. Well, how can we get around getting good spectra? And it's called poor man's spectroscopy, is again using standard filters. And again, here are standard filters from from Bader, and these standard filters are the Johnson UB, VR, and I, with B and V being the most common, and we can see them installed on the back of a telescope here. So a telescope would simply take a picture through that filter, and the camera itself would not be a color image. It would take a black and white image, meaning recording all the photons that it receives and not photons of a given wavelength in a given region. See, a color camera looks at, it does this filtering process for you, meaning if it lands on this pixel and that pixel is sensitive to green, then you'll get a green pixel, or light there. And if lands on the pixel that's sensitive to red, you'll get a little bit of a hotspot of red on that image. But most astronomical imagery says, give me a really even response across all wavelengths, and I'll put a filter in front of it, and then I'll only be looking at the red or the yellow or the green or the blue light, and then I'll reconstruct the color image post facto from this image. That's usually how it's done. So given that that's how it's done, the B and V filters tend to be the ones that are used more frequently, and in fact the V is dominant for variable star observations. So the difference in brightness, again, can be measured in 2 filters, and that determines also the temperature of the star. So if we standardize things and use the most common, which are the B and V filter, we find that the B and V filters, really the difference in brightness between, say, the blue line and the yellow line that we see here across these spectra, we can see that they definitely show the color and therefore temperature of the star. So let's take our most important star cluster in the entire sky. This is the Hyades. And it's kind of hard to see the Hyades in this image, but it's an overdensity of stars that lies at the center of this image. So this image includes, if we look carefully, the center of the Taurus the bull, and the V of Taurus the bull is inside of this group, and that is the Hyades. So if you look at the head of Taurus the bull, that is the Hyades star cluster. It's approximately 153 light years away, or 47 parsecs. And the real trick for getting the distance to the Hyades is determining which of the stars in this field is actually part of the Hyades. So extended studies for parallaxes and proper motions need to be done for the Hyades in order to determine who is a member of the Hyades. And also spectroscopic studies are important too, because that tells you about composition as well. So the Hyades star cluster is in the center of this diagram. You could kind of see that it fades away off to the left, and you can see, oh, there's an overdensity here and an underdensity there. And that's what we mean by a star cluster. If we then calibrate and look at the Hipparchus data and the TICO data and some other data from another group, and we combine them together and filter out all the stars that have roughly the same distance, roughly the same parallax, and roughly the same proper motion, then we get what's known as an HR diagram for the Hyades. And what we're measuring here is the Johnson B filter minus the brightness in the B minus the brightness in the V. So that's the color across the bottom, and that's what this graph is reading. And the left-hand side is the apparent magnitude of the stars, not the absolute magnitude, but the apparent magnitude of the stars that we're looking at in the V filter. So this is called a color magnitude diagram, where color is on the bottom and magnitude is on the left. And remember, magnitudes, a difference in 5 magnitudes is 100 times brightness. So there are some stars in the Hyades that are magnitude 5, and there's some that are magnitude 4, and even a couple that are magnitude 3. And so magnitude 4 and 3 stars are visible to the naked eye. In fact, most of the ones in the upper left-hand corner of this thing are naked eye stars. So when we look at the Hyades in the sky, we see maybe 15 or 20 stars, and they seem to be grouped in the sky. And that's the upper left-hand corner that we're seeing. So those are the brightest and the bluest of the stars. And we see a distinct main sequence going all the way down to magnitude 16 or 17 with the deepest red stars, red dwarf type stars, and some white dwarfs also in the lower left, and a couple of giants in the upper right. So when we look at the Hyades, we got a few red giants, a bunch of blue hot stars, and that's what we see with our eyes in the sky. But what deep study actually shows us that there's a lot more there. So what we can do then is now we have a main sequence. And since we have a main sequence and we have a distance to the star cluster, we can use that. And therefore, remember, brighter goes up to the left and hotter goes left, gets hotter to the left as well. All right, how can we use that? And now we can use this idea of a calibrated cluster from first getting the distance to the Hyades. We can now use that to go get the distance to the Pleiades. How can we do that? Well, all right, so we now know that stars are roughly the same thing, and we know that the Pleiades has a main sequence too, and I'll show you that in just a second. We will find that it also has a main sequence, and the more stars that we can get that are members, we get a tighter main sequence. We get we can eliminate the ones that we know are not part of the cluster, or even just ones that seem to be outliers and we're not really sure about them, so we just ditch them. That's frequently what happens. If you get some bad data, you just kind of dump it. And there's nothing wrong with that. If you're not sure about your data, why would you keep it? All right, so the equations that we're going to use are on the top one. The top one shows the brightness of, say, one star, B sub 1, compared to the brightness of another star, B sub 2. So we say, how much brighter is B1 compared to B2? And that's strictly dependent on their distances, given that they're the exact same kind of star. So two stars that are exactly the same, but are at different distances, number 1 and number 2, distance 1 and distance 2 for the same brightness of same type of star. How bright they are is dependent on their distances. So the inverse square means that if one star is 10 times brighter than the other, then it must be the square root of 10 times, or well, let's make it easier on ourselves. Let's say the brightness of 1 is 100 times the brightness of 2, and they're exactly the same type of star. Then therefore, number 2 must be 10 times further than number 1. That's what that top equation says. But our more important thing is that we can actually shift that into brightnesses again and look at two different or the same kind of star again. And instead of turning in terms of brightness, meaning how many photons per second, we can use astronomical magnitude. And that's what M1 and M2 are in the middle equation. So if you take the apparent magnitude, and the lowercase m for magnitude is always magnitude. Sorry, not mass, magnitude. Magnitude shows yeah, I know. You're going to see this a lot. Which is it, mass or magnitude? But when we talk about brightnesses and star measurements, we're going to be talking about magnitude. So sorry about that. But off we go. One of the wonderful things about astronomy is that you get to use the same thing for magnitude as mass. Whoops, off we go. So imagine again, it's the same kind of star, and they have different apparent magnitudes, m sub 1 and m sub 2. The distance modulus equation, we're getting really close to that, or the difference in brightness, and we define magnitudes are. Now we take the distance between them, distance 1 compared to distance 2. It then is the log base 10, or the base 10 logarithm of the ratio of those two distances, yuck, times 5 is equal to the magnitude difference between the stars. And in fact, that is the definition of magnitude right there. And the distance here now is in parsecs. That's how we're going to be actually defining things in terms of parsecs. So now we didn't say what the distance measurement is. In all of these cases, all three equations, the distance is in parsecs. So now let's play an interesting and important game. We've always been using the same kind of star. We said, well, it's at some distance or whatnot. We take the star, and what if it's 10 times further? What if it's 100 times further? What if it's 10 times closer? Blah, blah, blah. But now we're going to fix it at a particular distance. Let's pretend that we can move the star, and that we'll make a reference point. What is the magnitude of the star, m sub 1, if d sub 1, the distance, is 10 parsecs? So if the distance to a star is exactly 10 parsecs, how bright would it be if it's closer than 10 parsecs or further than 10 parsecs? And that's where the capital M comes in. Again, not mass, that's absolute magnitude. So the absolute magnitude of a star at 10 parsecs is actually a reference of luminosity. Because if we pretend that all the stars are 10 parsecs away, then if they have a brightness difference, then that's an intrinsic brightness difference. So the last equation is called the distance modulus equation, and that tells you that, so now the distance to the object is in parsecs. Lowercase m is the magnitude or brightness that you measure in magnitudes. And capital M is absolute magnitude of it. So you somehow have to have a handle on the absolute magnitudes in order to get the distance. So that's what we're going to really play with. So what people have recently been doing with the Gaia study is actually really trying to finely calibrate this HR diagram just specifically for the Hyades. And this comes from April of 2018, and this is Stellareno and team. This is April 28th for the monthly notices of the Royal Astronomical Society, MNRAS. And I give the link here for you to go peruse. But this is a much, from the previous ones from Hipparchus data, this is from the Gaia data. And how we read this graph then is a little different than the previous graphs that we showed. Again, we have the Johnson B and Johnson V filter color, meaning the brightness in those two things. But now they've taken, as a result of knowing the parallax due to Gaia very well, we can now use the absolute magnitude in the Johnson V filter. That's what capital M sub V here stands for. The other two, the B minus V, are simply the magnitudes of the B and V filters. The left hand, the y-axis going up and down, is the absolute magnitude. And now we know the absolute magnitude because we know the distance to the star cluster because we have parallax, thanks to Gaia, which gave an incredibly good parallax. And the tricky thing is, notice that the error bars, which are the horizontal lines going left and right, show how well we know particular data. For bright stars, it's fairly easy. But for dim stars, it gets trickier because the B and V magnitudes are not well determined for dim stars. These are close stars, too. They're only 150 parsecs away, only 150 light years away, or 40, 50 parsecs. And even now, the magnitude difference for looking at an M dwarf type star, that you can see that it's really hard to measure their brightnesses because in standard filters, they're actually really dim stars, so they're hard to measure. And this was an incredibly important thing to do, is actually try to get this distance measurement. And that black line that kind of traces through it, we'll get to what that is, but that basically describes what that's an interesting thing that we'll talk about, but it relates to the age of the star cluster, and we'll talk about that later in future lectures. So here are the Pleiades, M45, and it has Messier object 45, sometimes called the Seven Sisters. It's about 400 light years away. The distance across this cluster is about 13 light years. The blue reflection nebula people think that it's actually, the star cluster is actually passing through this nebula and illuminating it, or at least illuminating it from behind. The star cluster is mostly in front of it, so it's a reflection nebula of material as the star cluster passes through it. So it's actually not thought to be part of the cluster. What's neat is that the Pleiades is in roughly the same direction in the sky as the Hyades. So if you pulled out from this picture and looked to, say, to the east of the Pleiades, you would see Aldebaran and the Taurus the Bull, and you'd see the Hyades as a V-type shape in the sky. So the Pleiades are are a nice little group, and sometimes people think that's a Little Dipper. It's not. That's not the Little Dipper. It's the Seven Sisters, and you get to see them in the sky. There are about 3,000 stars in the Pleiades, or Messier 45. And that lets us to say, well, if we got a cluster of stars, maybe they're roughly at the same distance. Yeah, let's see what we can use that for. There's another group of stars, another double cluster, the Perseus double cluster, about 7,000 light years away, which has been known for a long time. And if you get extraordinarily dark skies, you can see this with naked eye. It can actually be seen as just two little fuzzy clouds close in the sky. And through a telescope, it looks very, very pretty. So it doesn't look like this. This is a long exposure, but you get to see the two groups of stars in the sky. And they're roughly at the same distance. And they're only separated by a couple hundred light years, but at 7,000 light years away, they look close together in the sky. So now what we can do is we can take the color, the B minus V color, and plot it compared to the apparent magnitude, the apparent visual magnitude for both the Hyades and the Pleiades. And HRD here stands for HR diagram. And the blue dots are for Hyades, and the red dots are for the Pleiades. Now, stars are the same everywhere, and that's what we learn. And if we know the distances to the stars, we can calibrate the HR diagram. So the only reason that the Pleiades HR diagram is below and therefore fainter than the Hyades HR diagram is because all of the stars are farther away. So all we have to do is then say, how far up must we raise the Pleiades in order for it to match the Hyades? So they're the same things. They're all stars, and they're all A-type stars or B-type stars or M-type stars or F-type stars. The only reason that they're dimmer, meaning farther directly below, is that they're farther away. So that allows us to then say, if we calibrate the distance to the Hyades, and we want to know the distance to the Pleiades, all we have to do is measure their apparent brightness, V, measure their colors, B minus V, and then see what the difference is between the Hyades and Pleiades. And then we get the distance to the Pleiades, and that's how we know that the Pleiades are about 400 light years away, is because of that. So let's scroll back a bit, and that's right, about 400 light years away by looking at the HR diagram of the Pleiades. And that's where we get this thing from, is at that distance. So measuring the distance to the Hyades gets you to all these different star clusters, and star cluster after star cluster. In fact, another set of Gaia data, if you go Googling around, shows another group using the Gaia team to make like tens of HR diagrams of nearby star clusters, and putting them all together in order to calibrate an HR diagram for all stars. What's really fascinating is that this is a B magnitude and a V magnitude, and these are just brightnesses of stars. And once you have parallax, you can then get distances to almost anywhere by simply getting the brightness of stars in two filters, which you can buy online at Amazon and stick on the back of a telescope and go take pictures with. Doing the parallaxes is hard, but getting an HR diagram, or at least a color magnitude diagram, is not hard. That is something that is within the reach of amateur observers and college students, basically, or even dedicated crazy guys and gals who want to go out and buy a scope and actually try it. There's nothing stopping you except, well, money and time. Other than that, there's nothing really that's stopping you. It's doable and available for people to do. And you can do that because the Hyades and the Pleiades are both things in the sky that are easily visible. So a good amateur project over a summer or a late summer would be to do this. So we just take the Hyades and imagine that it is farther away and those two HR diagrams overlap. And when they overlap perfectly, that's how you know the distance to them. And we just use that distance modulus equation to show how far away they are. And once you have, therefore, the distance to the Hyades, and then you find them, and you can do a color magnitude diagram for any other star cluster, you then calibrate those things together. It assumes that the Hyades are a normal sample of stars. But the good thing is that they have a very long main sequence, and many other star clusters do too. And so the Hyades, being a little older star cluster, still has a good main sequence to actually match up with other clusters. And this is where we're going to go with this. In the very, very, very big thing, we're calling this the cosmic distance ladder. We're going to get out there very soon. And so here we see a good 8 things to kind of get us out to the distances. Across the bottom, 10 times distance each way. Parallax is our first thing that we use in order to get distances to stars. And then we can actually use proper motions and the groups of proper motions to actually show us how far something is. Because if it's running fast, it must be near. And if it's running slow, it must be far. But you have to have large statistical studies in order to do that. But our next set up there is main sequence fitting, or is the spectroscopic parallax solution for distances. And we see that the distance to the Hyades is critical for measuring all those other great distances that are way out there. And we're going to see in order to actually get the distance to the Large Magellanic Cloud, LMC, or M31, the Andromeda Galaxy, or the Virgo cluster of galaxies, or the Coma cluster of galaxies, we really need to get the distance to the Hyades extraordinarily accurately in order to finally get way up in the upper right the redshift. And redshift is eventually what we use in order to show the expansion of the universe in the Big Bang. So it's really funny that we start off with getting parallaxes to nearby stars, and this stepwise function of one thing after another eventually gets you to distances of the entire universe. All right. So what's really nice is that what do we mean by clusters of stars? And so the European Space Agency put together this really nice little video with the Gaia mission that shows us what we mean by a star cluster. And so we have our solar system, and I put the link down there so you can go get to it. And so the solar system, we zoom out and go farther and farther out and farther away. The sun becomes just one star of many, and we can see that we're going to aim at the Hyades, and the Pleiades is just in the upper right there. You can see it as we zoom around. And now we go and orbit the Hyades cluster, the nearest star cluster to us. And we can see that this is what we mean by a star cluster. You see all those bright dots with some glow around them? Those are the stars of the cluster. But we know there's many more stars that are much dimmer, but we're really kind of focused on the bright stars. And there's the Milky Way in the background. And with the Milky Way in the background, eventually we will use this star cluster to help us understand the distances to other star clusters and calibrate the HR diagram so we can get distances to this myriad number of stars that are existing in our Milky Way galaxy, which now we're zooming out of. And the Milky Way galaxy is composed of 200 billion plus stars, and it's about 100,000 light years across. And we're about 2/3 the way out from the center. There are numerous other objects out there in the cosmos, and our Milky Way is just one galaxy of millions. So I invite you to go take a look at the Gaia website, go take a look at these things, go take a look at all of that stuff. It's an amazing, amazing set of materials. So here's some review questions for you to kind of go over to see if you have it. And this is really what we're talking about today is distances. And distances to stars are really critical because they give us distances to galaxies, the size of our Milky Way, the size, and eventually the size of the universe. So spectroscopic parallax is the first step in that great, great, great quest. Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Well, we've gone through a lot of measurements, and we've actually alluded to a huge number of things that may or may not be occurring with stars. We've said that stars live, they have distances, they may even have run out of fuel. But we studied the Hyades star cluster in order to understand spectroscopic parallax, and we looked at the Pleiades star cluster to also help us with understanding parallax, but we really didn't discuss what the nature of star clusters are. So if we see in the background of this image, we just see lots of stars evenly distributed. But stars do not come evenly distributed, they come in clusters and groups as well. So let's look first at our friend the Hyades star cluster, which is the nearest star cluster to us at about 47 parsecs, or about 150 light years, not a million, 150 light years away. It's also pretty young, and its main sequence turns off indicates it's only about 600 million years old or so. So it's a young star cluster, and the cluster itself is kind of hard to see because it's so spread out because it's so near to us. So let's look at some other star clusters. And what do we mean by main sequence turnoff? We mean that there is a series of stars that are bluer than a certain value in the B minus V. And that turnoff will tell us the age of the star cluster. That is the trick for today. So I gave it all away, but let's develop that whole idea. Here is the Gaia study, which actually then shows, which we showed last time, which was that line that goes all the way across. That black line across is a computer simulation of exactly when the stars run out of fuel. And when they run out of fuel, specifically hydrogen fusion in the core, that top area, way up in the upper left, is where that kind of goes off to a squiggle sort of straggle. So you have the main sequence, which is almost a straight line going from lower right up to upper left, and all of a sudden it becomes a squiggly squiggle. That squiggly squiggle is what happens to the star when it runs out of hydrogen in its core. The exterior of the star changes in both brightness and color as the star leaves the main sequence. Once again, the HR diagram is the central tool for all astrophysics, and this is again the Hipparchus view of nearby stars, about 22,000 stars. And we don't see a main sequence turn off here because we're looking at a lot of stars. However, we do see a group of stars called giants and a group of stars called white dwarfs. And we're going to see where those giants and white dwarfs actually come from at this point. So star clusters, what are they? We're going to use star clusters to get us there. So star clusters are grouped maybe a few hundred stars to many thousands to hundreds of thousands, if not millions of stars moving together through space. And all the stars in the cluster are roughly at the same distance. So if you measure the brightness, you're measuring their relative luminosities, or how luminous they are with respect to each other. And because they're clusters, we're assuming they all have the same age of stars in that cluster, because we're assuming that they were all born together at once inside that cluster. Now, the other thing we're assuming is because they were all born at the same time, they roughly have the same chemical composition, meaning how much more of hydrogen and helium, all the other elements heavier than hydrogen and helium they have. And we also find that they have an enormous range of stellar masses. And it's that last point that really tells us a lot of everything about the star cluster. So the cluster provides snapshots. All right, so here's what we're going to look at. So we have two different types of star clusters that we've observed in the sky, open clusters. They're fairly sparse. They're not spherical distribution. They're a few hundred to 1,000 or so stars, a couple of parsecs of tens of light years in diameter. They have many blue main sequence stars and only a few red giants, and they tend to be relatively young at a few 100 million years. Now, globular clusters, on the other hand, are spherical. They have lots of stars, between 100,000 and about a million stars. They're about 10 to 30 parsecs in diameter, so they're a bit bigger than open clusters. And there are no blue main sequence stars, no O stars, no B stars, no A stars, no Fs, very few Gs, if any, and many, many, many giants and red giants. Their ages tend to be about 8 to 12 billion years old. So open clusters tend to be young, and globular clusters, open clusters are young, globular clusters are old. let's look specifically now at open clusters. The HR diagrams for open clusters show that they are young to middle-aged, meaning young to middle-aged is somewhere up to about 2 to 3 billion years, depending on how big they are. They have blue main sequence stars, very few supergiants or giants, and they have old open clusters, have a few red giants. That might be how you distinguish them. And you don't see any horizontal giant branch stars, which is a group of stars that are burning helium in their core. The youngest open clusters have gas clouds associated with them, such as maybe the Pleiades and others as well. But mostly you have to look at them in star-forming regions, which we'll talk about in a future lecture. So let's look at some of them. Now, what do we mean by a star cluster? Well, this is a really good way to begin the concept of a star cluster. And I grabbed this from Wikipedia from a guy who has his own website called Raw Astro Data. But this tells us a lot. Now, you think of stars as evenly distributed across the sky. And in a two-dimensional setting, you can definitely see there's lots of stars here. And we got some dark areas. Those are called dark nebulae. But we're really focusing on the overdensity of bright stars just below center. And that overdensity is called Messier object number 11. Named after Charles Messier, who made a catalog of such bright objects back in the 17th century. What we see here is a cluster. It is an overdensity of stars, or a grouping of stars that tend to be brighter or more prominent than the evenly distributed background stars. And that's what we mean by a cluster of stars. So this is a star cluster. And now we're going to take a look at a whole bunch of different star clusters in the sky. And if we do a zoom close-up of Messier 11, it has its own special name. It's called the Wild Duck, and it's about 2,000 or almost 3,000 stars, living at about roughly 2,000 parsecs, or about 6,000 light years away. And you can see it in binoculars as well. And its age has been estimated about 250 million years. That's older than the dinosaurs. So if this were in the sky, the dinosaurs would have been able to see this thing in the sky as it formed. And probably back then it had a star cluster, had a gas cloud around it from where it formed, such as the Orion Nebula. And now the triangular shape is where it kind of gets from it. It's these odd names that people come up with for astronomical objects are really fun and very historical. So if you go Google around, you'll find that there's all sorts of funny names, and the reason that it's called the Wild Duck, maybe it's because it's a triangle of flying ducks or something. And the guy, instead of calling it the Wild Goose Cluster or the Wild Robin or the Wild Duck, the Wild things, he just thought lots of ducks flying in a triangle. That's interesting. In any event, another prominent open cluster is the Pleiades, or Messier object 55. It's got about 3,000 stars in it, lives about 400 light years away. About 13 light years across is the group of stars that you see in the center. And there's a bright reflection nebula, that's that blue glow, that's wispiness around it. And that's because the star cluster is passing through that nebula. And as it does so, it illuminates that nebula. All right, there's another example, is one of my favorites that you can go see in a small telescope, the Perseus double cluster, or NGC 869 and 884. It's two clusters that are approximately 7,000 light years away. And it's been seen for a very, very long time. And it's been noted, it was even noted by the astronomer Hipparchus, who gave us the name for the magnitude system, as well as giving us the idea about looking for brightnesses of stars. Those two clusters are separated by a couple hundred light years and are much younger, and many of the stars that are much younger and hotter than the sun. So let's zoom out and look at another star cluster, M67. That M11 was a very, very deep photograph, so it kind of masked what we would think about it. And M67 contains about 500 stars, and it lies almost 3,000 light years away in the constellation of Cancer. And with this, so if you're looking at this, that group of stars, that cluster in the center, is about 12 light years across. So that's kind of a dense little downtown sort of area. And that's what that's another kind of open cluster. Notice there's some space between them. Another name for open clusters are galactic clusters, because they're always situated in the galactic plane. So another one is Messier object number 457, and it's an open cluster in Cassiopeia. And we see a whole number of them. There's some bright stars in the center there, and the overdensity of stars there. The age of this one, it's a relatively young one, about 21 million years. So it was not visible if you went back 60 million years. You wouldn't be there in the sky. And it's almost 8,000 light years away. And there's a few thousand stars. In general, open clusters are up to about a few thousand stars, and they're formed from the same giant molecular cloud, and they have roughly about the same age. So let's look at let's look at NGC 663. It's another open star cluster, about 400 stars. That's that overdensity in the center with the bright center stars there. Its age is about 20 to 25 million years. And stars of spectral class B2 or higher, the O's are gone, are gone, but B2 are reaching the end of their main sequence lifetime. The open star clusters are generally mutually gravitationally bound. But as they move through space, there's lots of stars out there. They eventually get kind of close to maybe some other star clusters, so they get disrupted. And even the stars inside of a star cluster themselves can swing around each other and get flung out into space. And so eventually star clusters disperse. And here's another prominent one, Messier 36. It's about 4,000 light years away, about 14 light years across, and it's got at least 60 members in it. And it's similar to the Pleiades. And if it were that distant, it would be about the same brightness in the sky. Now, such star clusters only survive as their trip around the Milky Way a few hundred million years before the stars get dispersed because of that. And open clusters are also only found in spiral-type galaxies, which is where star formation occurs. So they are centered in star-forming locations. Once again, there's number Messier 41, one of the most prominent in the sky. If you look in the big dog, Canis Major, it's about just really close to almost exactly south of the bright star Sirius. So if you want to go find an open cluster, find the brightest star in the sky, Sirius, which follows Orion in the sky, and then just take 4 fingers widths due south from it, and that's where it is in the sky. There's about 100 stars, a number of white dwarfs, and a bunch of white dwarfs and red giants in there. And we have the average Doppler shift shows that it's rushing away from us at about 23 kilometers per second. And the diameter of the cluster at that distance is, well, not at that distance, but the diameter of the cluster is about 25 or so light years, and it's about 100 million years old. And all these pictures that I've shown you in the past bit have the same proportion, the same kind of black and whitishness. That's because I downloaded them from the Digital Sky Survey. That's part of the MAST project at the Space Telescope Science Institute. So the Mulcahy Astronomical Survey Telescope, or MAST, and with the Space Telescope Science Institute's digitization of the Palomar Digital Sky Survey allowed me to take these interesting images and download them and pull them in. And notice all of these images that are labeled with the MAST Earth Survey, I used the size of approximately 60 arc minutes on a side. So these are 1 degree by 1 degree images. So if you were to actually go outside and hold your thumb out at arm's length, your thumb is about 1 degree across. So each of these images is literally a thumbnail in the sky. And you can see just how big they are. All right, so the next kind of cluster is called a globular cluster. HR diagrams from this show that they're about 10 to 13 billion years old. So they're incredibly old. They have big red turnoffs, and there are absolutely no blue main sequence stars. None. There are no O, B, A, F, or G-type stars in any globular clusters. There are tons of red giants and no supergiant stars. And there's an incredibly prominent horizontal branch. There are slightly bluer and fainter main sequence stars, and they are slightly fainter main sequence stars. Why? Because they have less metals. Metals means any chemical element heavier than helium, such as carbon, nitrogen, oxygen, and they are that lower metallicity is a distinct difference in population, which we'll see when we talk about the Milky Way itself. So let's do a sample of globular clusters. Globular cluster M55 is in Sagittarius, and it's over almost 18,000 light years away. And again, these images are from the DSS, from the Space Telescope Science Institute, and they use the same proportions, about 60 arc minutes on the side, so you can see how big they are. So each of the open clusters is about the same angular size, but notice that because these things are much more distant, they're much, much, much larger. This particular globular cluster is about almost 300,000 times the mass of the Sun, and it has only about 1% of the carbon, nitrogen, oxygen that compared to all the stars that are close to the sun or in open clusters. So they're distinctly different stars. NGC 2808 is another globular cluster in the constellation Carina, visible from the southern hemisphere, and it's one of the most massive clusters. It's about 1 million stars, and it's about 12.5 billion years old at a distance of 30,000 light years, or about almost 10,000 parsecs. Yes, it looks small on this degree by degree on a side image, but that belies the density of stars that are situated inside of that. And the total mass of this object is about 1.4 million times the mass of the sun. So this thing is a real seriously massive object with lots and lots and lots of stars, and it's ancient. Okay, so M92, Messier 92, is a globular cluster in the constellation Hercules at about distance about 30,000 light years. So it's not as massive or as bright as the previous one, as NGC 2808. But it's a Messier object. But it is one of the more bright objects in terms of its absolute magnitude. It's also one of the oldest, and it has a mass of over 200,000 times the mass of the sun. This is a picture I took myself. I took this using the eye telescope, remote observatories, and this is of the Great Globular Cluster Messier 13. It's in the constellation Hercules, and it's a wonderful thing to go see, and it's definitely a binocular view, and we see two bright stars on either side of M13, and even a little galaxy just off to the right. And there's other fuzzy features in there that are also other galaxies too. But the globular cluster is dead center, and it's got some variable stars in it. And with that variable star that's embedded inside of the globular cluster can be made out with large telescopes. It's about 22,000 light years away and about 150 light years in diameter, and there's about a few 100,000 stars in it. And the globular clusters are so dense in general that if we were inside of them, if the sun were inside of them, somehow orbiting some distant star, then we would never experience night, because the sky would be so bright with so many stars. And here's an interesting globular cluster, M80 in Scorpius, about 30,000 light years away, about 100 light years in diameter. And what's interesting about this one is it's got a lot of blue stragglers, meaning stars the cluster itself is so incredibly dense that stars can actually collide. And when they collide, that makes them more massive. If that makes them more massive, that makes them bluer, that makes them hotter. And this particular study by Dr. Scherer at the Museum of Natural History, using the Hubble Space Telescope, actually shows the color of globular clusters, which tend to be much, 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 much redder. And that's a real critical thing that we look at. And I did actually a very interesting lab activity that details how you can actually make an HR diagram from the data that Dr. Scherer collected from the Hubble Legacy Archive. So send me a note if you want to do that lab on your own. Messier Object 9, well, we're looking really deep into the center of one of these things, is a near globular cluster. And again, now this is not a 1 degree by 1 degree. This is a close-up picture taken, and the credit is from the National Optical Astronomical Observatory, or NOAO, for this particular thing. It's about 5,500 light years from the galactic core, so it's really near to that thing. And its distance is about 26,000 light years away, and very, very bright compared to the sun. And there's lots of variable stars have been found. So it's interesting that variable stars are present in large numbers in globular clusters, but not so much in open clusters. But this is a big one though. This is Omega Centauri, NGC 5139. It's about 16,000 light years away, and it's the largest globular cluster in the entire Milky Way. It's about 150 light years across and has over 10 million stars in it, with a total mass of about 4 million solar masses. Interesting that the mass is less than the total number, and that's because all the big stars are gone. And Omega Centauri is also distinctive in that it may actually be originating from a disrupted dwarf galaxy that encountered the Milky Way. Now, this is, again, back to the DSS Space Telescope Science Institute image. So you're looking at something that's about a degree across. This object in the sky is about half the diameter or 3/4 the diameter of the moon, or about half the diameter of the moon. So if you go to the southern hemisphere when Omega Centauri is up in here in a dark sky location, you can see this thing, and it looks like a fuzzy star in the sky. And that's what you're looking at, Omega Centauri. If we then check out the globular cluster 47 Tucanae and just look at this is a Hubble Space Telescope image and a study. So the big image is on the left and the study is on the right, and we see that most of the stars in Tucanae, 47 Tucanae, are red or yellow. And therefore, if we look at the HR diagram, and the left is the center downtown area of Omega Centauri taken by Hubble Space Telescope Group, we see if we make an HR diagram of those stars, we see a main sequence turnoff, we see red giant branch, we see horizontal giant branch, we see white dwarfs, but most of the stars are red. In fact, all of the stars are red. The reason they look blue in that left-hand diagram is because the image was taken with narrowband filters, and relative blue was taken compared to relative red. So a color magnitude diagram for a globular cluster such as M55 will have a main sequence, a rather thick, low red main sequence, and that main sequence will indicate mostly K and M type stars. And mass decreases down the main sequence. So low mass stars are there. So we have relatively low mass stars to begin with that are less massive than the sun, if it's going to be older than 10 billion years, and those things will be much smaller. So the red giant branch are extraordinarily evolved stars. They've dead and gone. So they're off the main sequence. They are no longer burning hydrogen in their core. Something has changed in them, and they have changed to become red giants. And some of the stars are blue giants, and those blue giants are a result of now they're not just burning hydrogen, but they're probably burning helium, and that's where and then we have the blue stragglers, which are, because this is a globular cluster and it's an extraordinarily dense environment, stars can collide together to form a new star, and those stars are more massive than their progenitors, and so therefore they are bluer and hotter, and they're called blue stragglers. And then we have a smattering of white dwarfs, which are dead stars. So what we look at with the main sequence is that you can read the cluster diagram. Now remember, in the main sequence, massive stars are hot, they have high temperature and high luminosity. Low mass stars are red and cool with low luminosity. And as we saw previously, on the lifespan of stars, main sequence lifetime depends only on its mass. Massive stars live a very short period of time. Low mass stars have a very long period of time. And the lifetime of the main sequence compared to the sun is roughly goes to the inverse of the mass compared to the sun to the third power, to the cube. So a 10 solar mass star lives 1,000 times shorter than the sun, and a 1.1 solar mass star lives 1,000 times longer than the sun. And therefore, low mass stars even take longer to form than high mass stars. Stars live a life, and that's what's interesting about all this stuff. Stars have a definite lifespan. And so why? Because gravity pulls it in and the heat pushes it out. And then eventually it runs out of fuel to create the pressure. As it ages, there are internal changes. Hydrogen becomes helium, and therefore there is no fuel left. And if that happens, the internal changes deep in the core have external consequences, meaning the star changes its brightness and changes its color. And as it does so, that means its position on the HR diagram changes. As a star runs out of fuel in its core, deep in the star, that changes how it appears to us in the sky, meaning its color and its overall luminosity. As a star cluster ages now then, if we think about individual stars, that's what we cared about before. So therefore, if we have a group of stars, all with the same age, the stars on the high mass of that happen to be formed in that star cluster, they form very, very quickly, and then the lower mass stars are still forming and don't quite get to the main sequence as the high mass stars form. The high mass stars burn through their hydrogen extraordinarily fast and become supergiants. And then the lower mass stars eventually run out of hydrogen in their cores, and they too evolve off the main sequence. So what that means is that as stars live and die in a cluster, the main sequence peels off the top, and then from the top left to the lower right as the cluster ages. So we're going to see three examples real quick here. The first is the Pleiades. And the Pleiades is, of course, that quintessential nearby open cluster. It's about 100 million years old. And that means only the most massive members, the O and B type stars, have even had time to live out their entire main sequence. And so the upper left-hand corner has a very, very, very beginning turn to the main sequence as they age off their main sequence. But the main sequence is totally in full on the lower right. And in fact, there are some that are still not yet make it to the main sequence. And that's what it looks like there on the lower right. It just kind of veers straight to the right rather than making a nice downward turn left. That means that stars that are incredibly red have not yet completely formed as full stars. And even if that means that the least lowest mass stars can take a very long time to reach the main sequence. Now, if we look at an older star cluster like Messier object number 67, it's estimated to be about half the age of the Sun, or about 2.6 billion years. And as a result of that, stars that are more massive than the Sun, roughly speaking, something about like stars like Sirius is more massive than the Sun, that will have evolved off to become a red giant. But stars less massive than the Sun have not yet had a chance to go, because the total lifetime of the Sun is about 10 billion years. So if something's 2.5 billion years, we're looking at things that are just maybe stars that are just about 1.5 times the mass of the Sun to about twice the mass of the Sun are evolving away from the main sequence in Messier 67. Now, where's the Sun in this diagram? If it were in M67, well, that Sun's absolute visual magnitude is 4.34, and its color is 0.71. So it would be firmly inside of the main sequence of M67. So that's where the Sun would be on this main sequence diagram. I'll use my mouse to kind of show where that is. That's roughly about here-ish or so. So we've got this little point here where the Sun would be, but the Sun is not in M67. It's not in that cluster. It would be another 7 billion years before the turnoff point gets down to it. So let's look at something that has done that. This is 47 Tucanae, another major globular cluster, and we can see the turnoff point is well deeper than the Sun's, and it's about 13 billion years old, and there's nothing that's redder than that, and all of the stars are evolved into red giants, and we're left with K and M type dwarf stars, and that means the age of the turnoff point means that if it's 13 billion years old, this globular cluster is truly ancient and was formed when the universe was only a few 100 million years old. So the stars here have seen the beginnings of the universe. So let's look at them in a group, and let's make a model star cluster. So let's pretend that we can follow a star cluster all the way from beginning to end. And once this star cluster forms, let's say we have a long time to watch it. When a star cluster is formed, the stars descend from their from protostellar times until they become main sequence star. And we're introducing a new term called the zero age main sequence, or ZAMS. And that's the moment when nuclear fusion starts in the star. We're going to discuss that in the future in protostars. We talk about that in the future. So the zero age main sequence is when the star moves, evolves, its exterior appearance gives indication that it's now on the main sequence. And at about 1 million years, we see that the reddest, coolest stars have not yet become main sequence stars. They're still collapsing, so they haven't turned on nuclear fusion in the core. But the bluest, hottest stars have. So at 1 million years, there they go. The most massive stars have evolved already, and that's what's indicated by the little red dot on the upper right. Maybe there's some star that was 100 solar masses, and it formed and is going to die in less than 1 million years. All right, so 10 million years later, the O stars have completely formed. They become red giants, but that's what we're indicating on the upper right. And the B stars are now evolving off to become giant stars. All the most massive stars, they've gone and done their thing. They become red giants. And now the B stars. And now some of the lowest mass stars are still descending to the main sequence, but the G-type and most of the K-type stars have also descended. All right, so now after 100 million years, the A-type stars are now evolving. The O stars are completely gone. The B stars now have become these red giants up to the upper right, and now we're left with the A stars now at the tip of the turn-off point. And now the M stars are just starting to get to the main sequence after 100 million years. And finally, after about 1 billion years, all the massive stars are gone. We're talking all of them. Now we're down left to the low mass stars, or F-type stars. And these are just the ones that are turning off. F-type stars are still more massive than the sun, but the B stars are now, the A stars are now the red giant progenitors, and the O and B stars are gone. And there's some remnant white dwarfs because some of the stars have become white dwarfs. All right, so now we've got the M stars be finally making it to the main sequence. And after 10 billion years, we find that the G-type stars are the ones at the base of the main sequence turn off. There's huge numbers of red giants, subgiants, asymptotic giants, all sorts of giant-type stars. White dwarfs are scattering everywhere, and the M stars make up the dominant amount of the main sequence. So we can see that there's a main sequence, a giant branch, horizontal giant branch, and the zero-age main sequence is when the star finally meets the main sequence location. So the main sequence turn-off point is really important because the main sequence turns off towards the giant stars. The main sequence turn off indicates the age of the cluster, and as a cluster ages, the stars turn off at the high masses. So it goes from the high mass turn-off point to the low mass turn-off point. Low mass stars again have redder colors, and the high mass stars have bluer colors. The color of the turn-off point is the indication of the age of the cluster, and vast computer simulations show that this is what happens when stars evolve, or when they run out of fuel and evolve into giants. So old clusters are redder and fainter turn-off points. So the conclusion that we can get from this is that cluster HR diagrams give us a snapshot of how stars evolve with time. And stars, which means that they change. One star will change from being a main sequence star to a giant. And the observations with clusters with ages from a few million to over 15 billion. Oh my goodness, that's my stupid typo. Not 15 billion, 13 billion, 13.2 billion years indicates that there's a lot of our picture from stellar evolution. So when we piece together the story, we see that it's incredibly important, the idea that there's actual stellar evolution, that what happens in the stars in the sky, what we get is that stars actually have ages, and there are consequences, observational consequences to the idea that as stars run out of fuel, in hydrogen in their cores, the external thing changes. So you can make a computer model that says what it should look like, and amazingly enough, that's what we see. So when we compare, say, the H in Chi Persei, the double cluster in Perseus, there's its turn-off point, and we see M80, which is about 12 billion years old, not 15. Goodness gracious, there's nothing that's 15 billion years old. That would be too weird, because the universe is only 13.2 billion years old. So, and we see a distinct group under there. In sum, there's a whole bunch of things that can be learned by looking at clusters of stars, and most importantly, we learn a significant amount of information about the ages of stars and how they do. So very soon, now we're going to be talking about how stars are born, how they live, and how they die. So we've talked much about this nature of what happens when they run out, but let's get into the real details on that. So we're going to go straight into, actually backtrack a bit, and look at how stars form, because we did indicate that, we've seen that, so we're going to take a diversion next time and look at the nature of stellar formation and the interstellar medium. Take a look at these review questions, have a great time, see if you can answer a few on your own, and we'll see you soon.